is nothing at all. I've been holding on to us through every rise and fall. Are you leaving me? Is that what you're trying to say? Please don't hide behind silence and walk away. What do you mean it's over? What do you mean we're through? I've been building all my tomorrows around me and you. If you're really leaving, look me in the eyes. Don't turn our story into silence and unfinished goodbyes. Maybe I heard you wrong, maybe I'm just afraid, but every little change in you makes my heart shake. I keep searching for answers inside every word you say, hoping this isn't the moment you choose to walk away. Are you leaving me? Tell me it isn't true, 'cause I still can't imagine a world without you. If this is really goodbye, then why does my heart still stay holding on to the version of us that never walked away?
I wanna go back in time, back, before you stop being mine. Running through old memories, like a movie in rewind, looking for the moment where I lost your mind. I wanna go back to yesterday, back before the distance grew, back to the nights when hearing my name still meant something to you. I wanna go back and hold you closer before we slipped away, before goodnight became silence and you stopped staying. Back, take me to that time. Back, before goodbye arrived. I wanna go back and keep you. I wanna go back and try. But I read somewhere the tighter you hold, the faster goodbye arrives. The more you try to keep somebody, the more they slip away. So tell me, what am I supposed to do? How am I supposed to stay? Yeah, they say let it go, they say set it free. If it belongs with you, it'll come back naturally. But how do I do that? How do I act okay when every road I'm walking on still leads me away? I know love ain't ownership, I know hearts ain't chains, but knowing that and feeling that are two different kinds of pain. Maybe love is watching someone walk beyond your sight and still wishing them happiness every single night. Back, I can't go back in time, so I'll carry all these memories and slowly leave them behind. But tell me one more time, how do I stop loving you when I still don't know how to stop missing you? Stuck with you, and I kinda like it. You got a seat in my head, rent free every day. I try to kick you out, but you found another way. Late night headphones on, walking through the city lights. Somehow every little road still takes me to your side. No rush, no pressure, stay a little longer right here. I'm stuck with you, and I don't mind. Stuck with you all all the time. Stuck with you feels so right. Baby, stay tonight. Maybe I'm addicted to the way you smile. Maybe it's the way you make the world worthwhile. Maybe I don't need a million things to do, 'cause every little moment feels better with you. Coffee in the morning, your name in my head. Funny how I hear your voice and things you never said. Everybody tells me I should play it cool, but every time you text me I turn into a fool. Slow down, lean close, don't say goodbye yet. Stay here just a little longer. I'm stuck with you and I don't mind. Stuck with you every night. Stuck with you feels so right. Baby, stay tonight. If being stuck means I get to stay with you, then I don't need saving. I like the view. Stuck with you.
마이크 테스트 하나 둘 마이크 테스트 하나 둘 좀 땡큐 네. 아, 네, 알겠습니다.
Living there too long, so put on something brighter. Even if I fake a smile, maybe my heart will follow after a little while. The sky feels kinda heavy, my thoughts are everywhere, but maybe a happy melody can clean the air. Play me something happy, even if I'm not. Play me something sunny for this cloudy heart. I wanna dance in my room, even if I don't feel like dancing. Sing along to the chorus, even if my voice is cracking. Maybe happiness is weird, maybe it arrives this way, through a silly little song on an ordinary day. La la la, I don't have to be okay. La la, not today. La la, but maybe I can borrow a little happiness from this song. Play me something happy, turn it up loud until my tired little heart starts singing out. I don't feel that good today, but maybe that's alright, 'cause sometimes a good song can carry you through the night.
Breaking news, breaking news. Your smile has been reported inside my head again. I try replacing you with hobbies, water, sleep, healthy decisions. None of them work, now my plans know your name, and my coffee misses you. My therapist would probably say that's unhealthy. My playlist says track 7 reminds me of them. Guess who I'm listening to? Emergency, emergency. My heart has escaped again. Emergency, emergency. Please return it to sender. You said I was attractive, cool, funny, different. I'm investigating a missing person case, 'cause the version of you that like me has disappeared without a trace. Evidence A, you call me first. Evidence B, you stayed till 3. Evidence C, you smiled at me way too suspiciously. Now you're acting innocent, Your Honor, I disagree. I've got screenshots, memories, and emotional receipts. Case file open, no conclusion. Heart confused under review. Please wait. Emergency, emergency. Who stole your feelings away? Emergency, emergency. 'Cause they were here yesterday. If you find the person who said I was amazing, tell them I'm still waiting. statement. Yeah. I've been right here the whole time. I'm standing next to you like I always do, but your eyes keep looking for somebody new. I'm right here talking, but you're looking past me like you're waiting for a story that hasn't happened yet. I know all your favorite songs, your coffee order too, but somehow that's not enough to keep your attention on me. I'm right here, right here, right here beside you. Why you looking for somebody new? Yeah, I've always been here through every high and low, but you keep waiting for a feeling you already know. Maybe you're searching for fireworks while I'm the steady light, and maybe that's why you never see me right. Yeah, yeah. New face, new name, same conversation, same game. You're looking for a miracle, I'm sitting in plain sight. You keep chasing shooting stars while I'm here every night. Maybe I'm too familiar, maybe that's my crime, 'cause people stop noticing what's beside them all the time. Look left, look right, look closer, I'm still here. Look left, look right, what are you waiting for? I'm right here, right here, right here beside you. Why you looking for somebody new? One day you'll realize the thing you've been searching for was sitting right beside you the whole time.
Lying in my bed tonight, full screen lighting up the dark.
Something doesn't feel right.
You don't call me anymore like you did before.
And my heart keeps knocking on a closed door.
Maybe I'm overthinking, maybe I'm not.
But why does it feel like you forgot what we got?
I lay down trying to sleep, but thoughts of you won't stop. Somehow I feel you talking to somebody else a lot.
I wanted you to talk to me the way you used to do.
Late night calls and little jokes, just me and you.
Why don't you call me
Lately, why don't you stay?
You used to tell me everything.
Now you're drifting away.
I think you made a mistake.
You forgot about my heart.
You forgot the way I loved you
From the very start.
You silly fool, can't you see
what you're putting me through?
I wanted all your attention, but
Now I'm losing you.
hold up, wait, tell me what's going on. Used to hear your voice every night, now the ringtone's gone.
I keep checking my phone like it's gonna change,
but the silence every night feels exactly the same.
You said forever once.
Remember that line? Now I'm sitting here alone at 9:15.
Maybe it's jealousy,
maybe it's love.
Maybe I just miss the days when I was enough.
Why don't you call
me lately? Why don't you stay?
Every little thing about us
feels further away.
I know I can't control you.
I know that's true.
But tonight my heart keeps wishing
you think about me too. You silly fool.
You forgot to think about me,
didn't you? tonight. Phone screen lighting up the dark.
Something doesn't feel right.
You don't call me anymore like you did before.
And my heart keeps knocking on a closed door.
Maybe I'm overthinking.
Hi everyone. Before starting, I just want to let you know that this meetup has been mainly organized by Instruct.KR, which is the local machine learning community that has been like just grown from the Seoul, but not limited to this place. So I just really want you to recommend to to join the Instruct.KR Discord. You can just like type this URL into your Safari or whatever your web browser, then it redirects to a Discord server. I just want you to wanna join before like attending this meetup. Instructor, that's a URL. Thank you.
I think you made a mistake.
You forgot about my heart
You forgot the way I loved you.
from the very start.
You silly fool, can't you see?
What you're putting me through.
I wanted all your attention, but
Now I'm losing you.
hold up, wait. Tell me what's going on. Used to hear your voice every night, now the ringtone's gone.
I keep checking my phone like it's gonna change.
But the silence every night feels exactly the same.
You said forever once.
Remember that line? Now I'm sitting here alone at 9:15.
Maybe it's jealousy.
Maybe it's love.
Maybe I just miss the days when I was enough.
Why don't you call me?
Me lately, why don't you stay?
Every little thing about us
Feels further away.
I know I can't control you,
I know that's true.
but tonight my heart keeps wishing
You think about me too. You silly fool.
you forgot to think about me.
Didn't you?
Can somebody tell me what matters most in life? Is it money? Is it love? Or chasing dreams all night? Everybody's got an answer. Everybody's got a view. But the older that I get, the less I seem to know is true. Tell me, what should I hold on to when everything keeps changing? What am I supposed to do? Is it love that really matters? Is it time we can't get back? Is it people standing by you when your whole world fades to black? Can somebody tell me before another year goes by what matters most in life? Before I say goodbye. Yeah. Everybody running, everybody chasing, trying to be somebody, trying to make it. Money in the bank, but the heart's still empty. Crowded room around you, but nobody gets me. So tell me, what's the answer? What's the thing worth keeping? The things we lose while living, all the dreams we're always seeking. Maybe it's the moments, maybe it's the people. Maybe life ain't something complicated. Maybe life is simple. Can somebody tell me what matters most tonight? 'Cause I'm still searching for the answer under these city lights. Wait a minute, hold up. before it's too late. You keep acting cool like you don't really care. Meanwhile, I'm over here fixing up my hair, checking every message, every little sign, wondering if someday you'll finally be mine. You think I'll always wait, same place, same time, but hearts keep moving forward just like the tide. One day I might wake up and not look for your name. One day this whole feeling might not feel the same. Tick tock, my heart keeps running. Tick tock, the clock ain't stopping. Love me, love me, love me first, before my feelings reverse. Love me, love me, love me now, before somebody else figures me out. Before my heart moves on, before the seasons change, before your name stops living inside everything. You better tell me now, you better make your move, 'cause I won't stay forever waiting here for you. Yeah, you keep saying maybe, I keep saying why. Yeah, you keep looking away when I catch your eye. Everybody notices except for you somehow. Or maybe you already know and you're just scared right now. Hey, 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 what's your plan? Hey, 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 do you understand? Hey, 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 I don't wanna be your baby, I wanna be your baby. Love me, love me, love me first, before my feelings reverse. Love me, love me, love me now, before somebody else figures me out. One day I might stop waiting, one day I might stop trying. So if you really want me, if you really do, love me first, before I stop loving you. To know how I feel when we're talking to someone else. I sit there smiling quietly while fighting with myself, trying to act normal, trying not to care, but my heart keeps looking at you over there. Maybe it's nothing, maybe it's unfair, but every time you laugh with them, I wish I was there. Do you know, do you know, do you know how that feels watching you give someone else the attention I still need? Yeah, you probably don't notice the way I go silent when you're talking to somebody new. Like I'm becoming invisible. I know I don't own you, I know that's the truth, but my heart gets jealous anyway, and I don't know what to do. Yeah, yeah, I know it's not a crime, I know you're free, but tell me why every time I see you laughing with somebody else, my whole mood leaves. I keep saying it's okay, but it never really is, 'cause part of me still wishes I was your favorite conversation. Maybe I'm selfish, maybe I'm weak, maybe I just miss when you looked at me that way. Do you know, do you know, do you know how that feels watching you drift away without even realizing it? You probably don't know. You probably never will. How one small conversation can break a quiet heart. Sugar, honey, baby, that's all. I don't need 1,000 I don't need a perfect line. If you're standing next to me, everything feels right. Slow down, come close, stay here all night. Late night conversations playing through my room. Your name sounds better than my favorite tune. Got me thinking about you lately. Got me feeling kinda crazy, sugar, honey, baby, that's all. That's enough for me to call it love. Sugar, honey, baby, that's all. That's enough to make my heartbeat rush. You don't have to promise forever. You don't have to say too much. Just stay right here beside me and I'll know it's love. Yeah. Low lights, midnight. Your shadow in my room, got your name floating slowly like perfume. No pressure, no drama, no games to play. Just me and you vibing till the break of day. Sweet like honey, dripping slow like an old cassette. Every little moment with you is my favorite, yeah. You're my favorite mood lately. Got me floating, baby. Sugar, honey, baby, that's all. That's enough for me to fall for you. I've been right here the whole time. I'm standing next to you like I always do. But your eyes keep looking for somebody new. I'm right at talking, but you're looking past me like you're waiting for a story that hasn't happened yet. I know all your favorite songs, your coffee order too, but somehow that's not enough to keep your attention on me. I'm right here, right here, right here beside you. You looking for somebody new. I've always been here through every high and low, but you keep waiting for a feeling you already know. Maybe you're searching for fireworks while I'm the steady light, and maybe that's why you never see me right. New face, new name, same conversation, same game. You're looking for a miracle, I'm sitting in plain sight. You keep chasing shooting stars while I'm here every night. Maybe I'm too familiar, maybe that's my crime, 'cause people stop noticing what's beside them all the time. Look left, look right, look closer, I'm still here. Look left, look right, what are you waiting for? Right here, right here, right here beside you. You looking for somebody new. One day you'll realize
Hi, everyone. Good afternoon. Let me start this event. Thanks for coming. And I'm Youngjun Jang from Instruct.KR and Korea University. I'll be organizing this AI Search Technology Meetup in Seoul with Max Buckley and Exa and Instruct.KR. So thanks for coming. And I'll start with the opening talk. Welcome to this event. So first, introducing our organizers. It's me and Sigrid. Sigrid is right in the second floor right now. And in front, there's Max Buckley here. Say hi to everybody. And he's from Exa, and he's a head of research at Exa AI. In the front, there's Sangtae Hong. He's my researcher. Eh? Oh, 죄송합니다. Sorry, I forgot to turn off the song. In front, there's Sangtae Hong. He's from Korea University also, and he's a PhD. He's in PhD course. And if you would like to network with him or everyone, just is welcome. First, I would like to introduce Instruct.KR. It's Korea's leading AI community. We have 10K, more than 10K members and 200K visitors. We have a lot of activities in this community. We share some weekly paper reviews. We focus on DeepSeek or LLMs or agents, or I work on search and information retrieval systems. And we also do a lot of open projects, such as Logic Core or Korean Chatbot Arena. And Logic Core is a really famous LLM multi-turn evaluation framework in Korea. So everyone use this as a benchmark. And we also do a lot of open source contributions. Like we have a lot of GitHub repositories. For example, we have Logic Core or BV25, and we have this Reanchor simple benchmark. We benchmark a lot of things that we can do in Instruct.KR. Also, Instruct.KR is a Discord community. So if you entered Instruct.KR in Google Chrome or something, you can just come into this community. We have a lot of channels here. We have general, Korean, or random, or I usually work on this awesome embedding re-ranker channel. I share a lot of papers. This is me. And there are a lot of people sharing some ideas or papers here. And we also have this community project here. So we do a lot of these kind of things in the community project. So we share a lot of ideas and we do a lot of projects here. So welcome to this community. We also have the English channel, so you can just join and speak in English in this channel. So the next is introducing Psionic AI. The Psionic AI is the company that hosted here and gave us the hall here. So there will be one person introducing Psionic AI. Please come and share.
Apologies for the late arrival. Hello, good morning, everyone. I'm Fabian Rowe, a researcher at Psionic's AI ML research team, and I'd like to share the honor of briefly introducing Psionic AI to everyone. Psionic AI is based on a mission of enhancing every conventional existing corporations into an AI agentic, AI native company, crafting AI agents powered by internal enterprise data. Our Storm platform fuses document understanding embedded with intelligent search, workflow automation, and agentic operations into a single AI adoption process. We also own Korean native AI research achievements from Korean foundation models, LLM interpretability, and multimodal understanding, which all becomes a solid foundation for our robust products applied in the real world. Ultimately, this aligns with our mission statement of establishing an open AI ecosystem, laying foundations for builders and enterprises to practical agentic AI. If you have any questions, feel free to ask questions within our break times. FYI, restrooms are located at the left rear side of the hall, and thank you so much. Please enjoy today's event.
Yeah, that was Psionic AI. Today's event, I would like to talk about this. Today's event, we have 4 sessions total. From session 1, we'll talk about retrieval model foundations. And session 2, we will talk about advanced RAG and retrieval. In session 3, we will talk about search applications and agents. And in the final, general models and others will be joining this session. So about today's event, we have prepared a name tag for networking. So everyone should have a name tag in their arm or in the chest, so that you can just know each other's names and know each other's affiliation, so you can network on break time or after this event. We also have 2 floors. On this floor, this is B1 floor. We have the burgers in the back and snacks in the back also. And also in floor 2, you can use the elevator. You can only use B1 floor and 2. And there's also burgers and Coke and a lot of snacks there. So you can just go up and eat. And we're going on live also on the second floor, so you can just see all those sessions to the television. Yeah. So the next is Max Buckley. He'll talk about search infrastructure fundamentals, roaring bitmaps, and advancing GPU vector search. Please welcome.
Thank you. Yeah, so my name is Max Buckley. I'm visiting Seoul for the first time from Zurich in Switzerland, where I work for Exa, leading a knowledge research team. So today I'm going to present some of the stuff I personally was working on, but to kind of give you a bit more flavor on Exa as a company. So Exa is building a search engine for AI, so search APIs kind of more specifically. So you're all obviously familiar with LLMs, ChatGPT or Claude. You know, when you're talking to it, oftentimes you'll see it doing these searches. It doesn't always show you exactly how it does these searches, but effectively that's calling some external web search service. Exa is one of those services, right? So, you know, effectively like Exa is building this sort of thing and trying to sell it to different businesses generally directly. I mean, you as a user can also build your own applications, but if you use Cursor, for example, Exa provides the search within Cursor. So when Cursor searches the web for documentation on PyTorch or whatever else you're building, that's using Exa. But as I say, I'll focus more on the kind of research that I've been personally doing. If anyone has any questions, feel free to interrupt me. I like to make these things kind of dynamic. Yeah, so click. Okay, so basically today I'm going to talk about filtered vector search. We're going to go a bit deep on some of the kind of specifics. So we're going to talk about roaring bitmaps, which is a particular compression format. We're going to talk, which is widely used in search engines and databases. So again, you may find this useful. If you don't know about these things, definitely I'll give you some primer, but I'll also point you to the papers that you can read. I'll talk about NVIDIA's CUDA vector search library, which is a GPU accelerated vector search library, which is sort of taking over the industry. So funnily, I was in Google until the end of February, and I was working with NVIDIA on their CUDA vector search in Google. I left Google and joined Exa on March 1st, and then was working with NVIDIA on CUDA vector search from Exa. And I'll be working probably with NVIDIA on this wherever I end up next. Yeah, so a lot of this stuff is work in progress, right? So it's not like, none of this stuff is published yet. It's not shipped. Some of it's in like pull requests or in like GitHub, so you can take a look at yourself. You can tell me what you think. And then finally, I'm going to talk about this idea that I was working on, which is called deep hybrid retrieval. So anyone here is pretty familiar with hybrid search. So we have this concept of lexical search, which is the sort of traditional search, right? Where you say red car and it finds the documents that have the words red and the words car in it. And exactly those ones. It doesn't find burgundy cars and it doesn't find red automobiles. Then, you know, circa BERT 2018 or so, we have this semantic search, right? Where we embed text and we kind of fuzzy match, right? Where we find things that are semantically similar. So a few years later, people realized semantic search is not a silver bullet, that it has like limitations, or there are areas where lexical search works better. And then people came up with hybrid search, which is where you take the two searches and union them and then kind of re-rank or upweight the results. But I'll talk about an idea we have kind of building on this. Yeah, so these are obviously Claude slides, just in case people aren't aware. But yeah, so first thing I want to talk about is this roaring bitmaps. And I'll first of all justify like why you should care about roaring bitmaps. So roaring bitmaps are used everywhere, right? So they're used in various search engines, in various kind of data formats, in databases. And what's nice about roaring bitmaps is if you have sparse data, if you have like incomplete data, it compresses them nicely and it finds the right compression based on the kind of cardinality of the data. And I've already kind of explained what I'm going to talk about, so I guess I'll jump to the next slide. Yeah, so what a roaring bitmap does is it creates this like 2-level index over your sort of integer set. So effectively what it does is it breaks your, like, so you have, let's say, some number of documents. You have like tens of millions of documents, right? And only a fraction of those tens of millions of documents contain the term you care about, red shoes, right? So, you have computed offline which documents contain the word red, and it's, let's say, 2 million of them, and which documents contain the word shoes, and it's, again, I don't know, 5 million of them. So what you need to do when someone searches red shoes in a sort of traditional search engine is find the intersection or the union, your choice, depending on the search engine, of these two sets, right? So that's either going to be up to 7 million documents if it's the union, or it's going to be 2 million documents if it's the intersection. And roaring bitmaps give you a really efficient way to do all of this. They give you an efficient way to store these things. So instead of storing like 200 million bits, or whatever I started with, 20 million, and saying, okay, only a few percent are ones and the rest are zeros, you can store this much more efficiently if you store this as like what's called an array list of the integers that are positive, or potentially later, as I'll talk about it, a run, which is when you have a sequence, right, of values. And this, additional compression means it becomes much smaller to store, but the compression here, and what's more important, is the structure makes it much quicker to do specific operations, right? Like effectively, the data set here is like self-describing. So rather than having 200 million bits that are all 0 or 1, you have the 200 million partitioned into sort of 65,000, 64,000 chunks, and each chunk has a particular type where, depending on the cardinality of that chunk, it will either be an array of sorted integers, it will be a bit set if it's dense, or it'll be a run if there's a kind of consistent sequence. And all of this information is stored in the data type itself. So you can use it very quickly at kind of serving time, which is when you want it. So, I mean, I'm not going into this in kind of great detail to sort of explain exactly how this works, but there is 2 papers that I would recommend checking out if you work on search at all, if you work on data sets. These are 2 really kind of foundational papers. One is, both of them are basically the roaring bitmap papers. The first one introduces the type without the run encoding, so it's basically array and bit set only. And the follow-on paper introduces the runs. What's particularly nice about this idea of runs is if you can sort your data, or if your data is particularly structured. So if you think about it, if you just have like a arbitrary query like red shoes, probably different documents mention red and different ones mention shoes, and that's not so useful. But if you think about a different query, like maybe you say, I want all the results from after July 25th, then you probably have a sequence of zeros until July 25th, and then a sequence of ones from July 25th onwards. And then you can use this kind of run length encoding, right, where you say basically all zeros, all ones, and you store it super efficiently, and then you can leverage this. Sorry, just to be clear, the reason I'm explaining all this is because this is what the GPU efficient implementations are going to work from. They're going to use the ideas of this sort of structure and the organization that's in the data to efficiently search the data later. Yeah, so the original paper introduces the 2 basic containers, right? This is the array container, right, which is a sorted list of integers. It's saying in this container, in this 65,000 elements, which elements are present. So this is going to be like 0, 1, 3, 7, or in this case, 12, 88, 301. And so this is for sparse chunks, right? This is going to be when you have like less than 6% or so, you can do the math, of the things are filled, right? And basically the idea here is that like it switches when the cardinality is like, if it's about being efficient, right? It's as small as it can be. And then you have a bit set, and the bit set is the kind of alternative to the roaring bitmap, as well as being part of it, right? Which is basically that all the bits are present. And yeah, so why 4096, right? So this is basically the switching point, right? And all of this is part of the format, right? So when you have roaring bitmaps, and you do like a union between 2, when you say, I want to get the red shoes, the roaring bitmap type handles this. It knows the cardinality of the containers. It merges the containers efficiently. So it knows the new cardinality, and so it will promote them to bit sets if they become too dense, or it will convert them to arrays if they become too sparse, if you're doing an intersection. All of this is handled for you super well by a very efficient sort of C roaring library under the hood. And again, it's very battle tested, right? It's used in, I think I had it on the previous slide, all of the different all of the different databases, vector databases, data processing systems. So yeah, and then the run containers were introduced in a follow-on paper. Consistently faster and smaller compressed bitmaps with roaring. And the reason these were introduced is because until this point, certain compression schemes which used runs would beat roaring bitmaps on data that was run heavy. Once they introduced this, then roaring bitmap kind of wins across the board pretty nicely. And again, as I mentioned, right, so if your data is consecutive, or if you can make it consecutive. So if you can sort your data, which very often you can if you organize it offline, right, then you can get much better performance out of a roaring bitmap because suddenly it converts to run length encodings. And so you see this on some benchmarks, right, where if you have the data in a random order, the roaring bitmap provides some degree of compression and some degree of performance uplift. But if you sort the data by like the concatenation of the different like filter labels and then rerun it, you can get like 20x speed up. So very important. Yeah, one of the things exactly here is, again, basically is this kind of the operations piece, right? Ops. So the roaring bitmap basically supports efficient unions, intersections, and that's kind of what you're trying to do with this kind of retrieval step. And so here you can see, right, if you have this consecutive run, right, where you have like 100 to 1099 and 3 like trailing numbers, if you did an array container, now you'd have 1003 2 bytes in 16s, you get 2 kilobytes. If you had a bit set fixed, then you're storing all of the useless parts, so it's 8 kilobytes. And if you have just 3 runs, you have 12 bytes, which is quite a bit faster. And again, this translates nicely to the GPU case, which we'll talk about in a second. So yeah, why it wins in practice. So one thing here is that the cardinality is known, right? So the roaring bitmap type stores its own cardinality. It doesn't store an overall like cardinality, but it stores it per container. So you're going to have like just sum over the container cardinalities to get the overall cardinality, which is a lot nicer than having to do like a pop count on the whole bit set. It also handles this sort of typed dispatch for different set operations, right? So it looks at like the cardinality of the 2 things and merges a smaller one to the larger one. It, merges things efficiently. If you have correct hardware, you can use these SIMD accelerated. And it's also like cache friendly, so it will fit in the kind of cache of your computer, so it can be quite fast, especially if you have like GPU case where it can fit in like your L1 or L2 cache, depending on your use case. So yeah, then I was going to talk about NVIDIA CUDA vector search. I'm going to bring that sort of together, right? So if you don't know, as I mentioned, CUDA vector search it's kind of seeming to become like a successor to FACE. If you use FACE, Facebook AI Similarity Search, that actually offers a CUDA vector search backend, or you can use CUDA vector search directly. And it's maintained by NVIDIA, although it's open source, so you can contribute to it, which is what I do here. And it offers not only kind of search on GPU, but also index building. So when I was at Google, the main interest in CUDA vector search was for offline index building. So if you have like a very large index, it takes a long time to build like a HNSW graph. But this is a task that can be kind of parallelized well on GPUs, and the GPUs can output a graph which can be reused on CPU. So you can use it for just index building and still serve on CPU if that's what you prefer. More recently, there's research from LinkedIn and also from ourselves at Exa using CUDA vector search for GPU-powered search, like to actually use the GPU at serving time to actually brute force a lot of the search. I mean, the GPUs are incredibly fast at this. I don't have exact numbers right here, but typically we shard approximately like 200 million or so elements per GPU, and you're talking, we can handle, I don't know, thousands of QPS on like one GPU in like 200 milliseconds or something. So it's pretty fast to do a huge number of computations. And exhaustive search is important here because it's going to be where I come back to it kind of at the end. But LinkedIn have also published, there's a very good paper from LinkedIn that I didn't cite, but you should check out, called Semantic Search at LinkedIn, which I think points in a lot of the directions the industry is going. And I think as GPUs get cheaper, especially the older GPUs, they can be used for this as well. And especially if you have the GPUs for other parts of your stack, right? Maybe you're using them for like model training, or maybe you have different jobs that can be kind of scheduled on them. You can use this. One thing that's very nice here as well is with GPUs, because you can do this exhaustive search quite fast, it's very nice for getting your like benchmarking, right? Checking your kind of recall versus your golden reference. So I was able to reproduce some of the DPR paper down the end of this, like, I don't know, in a few minutes, whereas it took a long time, I'm sure, to actually do it back in 2020. Cool. Yeah, so basically, what is the exhaustive search, right? So when I talk about vector search, I hope everyone here is familiar with the concept of like exact search, or like k nearest neighbors, or approximate search, or something that's called ANN. I won't dwell on ANN too much, but the idea of ANN, approximate nearest neighbors, is that you basically construct an index in advance, and that index lets you quickly get a good feel for the data set and find the data points that are close to the target and high quality. So effectively, you're doing a lot of compute at index building time to create this data structure that lets you find things that are pretty good pretty quickly. Of course, pretty good here, hand wavy. You trade some degree of recall for this speed, right? If you do exhaustive search, if you search through everything, there are advantages with this. The biggest one is you don't have to build or like maintain a search index. So as I mentioned when I was at Google, the main interest in using GPUs was to build these indexes, because when you have very big sets of items, the index build could become many hours on CPU or even days. So some of the bigger databases took days to build the index. That directly affects things like freshness, right? So obviously, if it takes a day and a half to build your index over 20 billion items, that means your freshest things are going to be like a day and a half old, plus there's going to be additional time to embed them and process them and whatever before that, right? That particular day and a half could turn into a few hours on an old GPU, or maybe an hour on a new GPU, which obviously means your freshness is a lot better. Yeah. So basically, what the exhaustive search boils down to is doing a matrix multiply, right? You have your query vectors, and remember, GPUs are massively parallel, so you can have lots of query vectors. So if you think about a search engine, your search query is not being looked up alone. There's lots of searches arriving. So then all of those get embedded and put into a batch, and then that batch of 1,000 queries is multiplied with the vectors of all of the documents. So this is a lot of compute, right? And then for every one of those query vectors, we're going to collect the top K, the best K results, right? Yeah, so basically typically this is done as a dot product. If you're doing like other distance metrics, you should check out that you can basically reduce things to a dot product. You can normalize the vectors in advance, and it makes things quite a bit faster in practice. Yeah, here was, I think, the number that we had. So like a 21 million by 768 dimensional corpus, exact top 100 for 22,000 queries in 27 seconds on my 5090 at home, which is pretty good because it would have taken like, I don't know, an hour probably back in 2020. But what's very nice about exhaustive search, and this is kind of the key point, right, is it composes cleanly with arbitrary filters, right? One of the challenges with ANN is you build this index in advance, not knowing like what filters the user will need. And you have the choice then to basically do pre-filtering, which is where you just say, okay, let's filter the data set down to this subset, and let's not use our ANN index. Or you do what's called post-filtering, which is where you do ANN and you retrieve more results than you need, and then check the kind of predicate after the fact. But that can leave you with an empty result set. If you do exhaustive search, then you are in fact looking at literally every vector, and you don't have to worry about that kind of loss of recall when you do filtering. So if you do look up ANN filtering problem, you will find like lots of articles, documents about it. It's not, it's not novel. But yeah, how does CUDA vector search handle this today? If we look at the exact exhaustive search, right? So today they support basically using a bit set. So you can use one bit set, one shared like mask for all of the queries in a batch, or you can use a bitmap, which is per query masks, right? So in the sort of former case, what we're doing is we're saying, for all my queries, ignore the deleted rows, for example, because the rows may be marked as deleted, but just physically still present on disk or wherever else. In this case, like the size of the mask will be kind of proportional to the size of your vector set. So if you have like 200 million vectors, as we often do, in one shard, you'll have like 125 megabyte filters. but to say the filter here is the same one, so it's not 125 multiplied by query number of queries, it's 125 total, right? On this side, we have a bit more of a challenge because now you're going to have one filter for every query. And this is where maybe some of the roaring bitmap story becomes clear to you again, right? With the roaring bitmap, if we have a sparse filter, like if we're like looking for something that only matches 1%, 2% of all the documents, that is no longer going to be 125 megabytes. It's going to be potentially 1, 2. It depends on the distribution, but it's going to be like a few megabytes. So it's going to be significantly smaller, and that's going to be especially nice over here in the case where it can be multiplied by the number of queries. It's also worth noting that the reduction in size also has some implications for the time to actually copy it, because you're copying physically the data from CPU RAM to GPU RAM. But yes, the interesting question here is, given a mask, how should the GPU actually skip work? Like, what should the GPU do to get more performance, right? I don't think I have a slide on this. Yeah, okay, I do. So basically, at the moment, if you look at the CUDA vector search library on GitHub, like on main, it's very far from optimal. Basically, what they do is they have this filter which basically says, you know, if things are like, if your selectivity is less than 10%, they do this sampled dense matrix multiplication, SDGMM or something. And if it's greater than 10%, they do a full matrix multiplication and then they post-filter it. So the reason I say this is far from ideal is because there's actually an intermediate option that they've kind of missed, is one of the failure modes. And the other failure mode is that 10% is way too high for this sampled dense matrix multiplication. Effectively, the size of the, so let me explain what that actually means. So when you do this SDDMM, there's no intermediate copy. So basically the GPU looks at the giant matrix and just looks up the kind of rows that you care about. But 10% is still quite a lot of rows. It doesn't copy them to an intermediate state and do a medium-sized matrix multiplication. Instead, it just does these individual multiplications. So it's using a lot of memory bandwidth. It's you know, not taking advantage of the hardware that NVIDIA provides, things like tensor cores. You know, once you go to the kind of greater than 10% and you're now doing the full matrix multiplication, then you're potentially wasting a lot of compute, because if you think about it, if you have 11%, you're doing, you know, however many multiplications you care about, let's say 10 million, and then you throw away, you know, 89% of the results. Ouch, you know? Saying that, this still works ridiculously fast and is much faster than whatever you're doing on your CPU. So, you know, some of these, like, maybe these feel kind of like details or whatever else, but these will hopefully change very soon because I have pull requests out for various parts. Yeah, so basically, I mean, this slide is just trying to get to the idea that, you know, there is a kind of a cutoff point, like where you should use this sampled dense matrix multiplication versus where you should use the full multiplication. But more importantly, as I'd say, there's a intermediate option that they somehow don't have right now, which is you can actually gather the rows that you care about and then do like a medium-sized matrix multiplication on those rows. So this means using some memory to copy the rows that you care about out of the giant matrix, but then you get to do a small or medium-sized matrix multiplication, and this will make your things run way faster in those intermediate size ranges. Yeah, I guess what's important in this graph is just that the cost of doing the kind of full matmul is constant, right? It doesn't change with size. The SDDMM, the sparse one, basically scales very poorly. So, and right now the cutoff point is completely wrong. Yep. But yeah, so I'll come back to that more on the results slide when I talk about how things kind of look when you kind of optimize it a bit. But yes, why am I talking to you about roaring bitmaps and GPU accelerated vector search? And basically the idea here is that the roaring bitmap knows its own shape, it knows its own structure, and we should be able to use that to make things faster, right? So one of the problems in CUDA vector search in general for all of the filtered vector search is the bit set doesn't know its own cardinality. So if you don't specifically pass the cardinality, it will count it at the beginning. So it'll do a kernel launch counting the cardinality and then decide what to do. So if we know that, we can skip that, or we can do more if we know more. And also remember, if you're building a search engine or a database, you are likely using roaring bitmaps already. You already have these things to hand. And so, passing them to your GPU as a bit set is just like throwing something away only to recompute it a few seconds later. And obviously that's not great. Yeah, so, as I say, like all of this is kind of things I've mentioned, right? So the roaring bitmap is storing the cardinality, right, per container. So it can quickly sum over to like 65,000 containers rather than summing over the 200 million bits, which is obviously faster. Array containers are already pre-sorted uint16 lists. So when I showed that SDDMM earlier on the right-hand side of the slide, it talked about what they were doing, right? And effectively what NVIDIA are doing is they first of all count the cardinality of this bit set, and if it's less than 10%, the next thing they do is they do a second pass and collect the indices that are non-zero. And effectively here, we already have them, right? We don't need to do that. And the other thing that we have here is that run containers are explicit like start length, right? So we could literally grab those and just do a mapmul of that entire submatrix. So that's nice. Yeah, so there's a lot of, I guess, opportunity here to make things a bit faster. So you're copying a smaller data type around, you're leveraging all of the internals, you're integrating nicely with existing kind of search stack and infra. Yeah, so for the different containers, we can do the different things, right? We can, as I mentioned, bit set effectively is the fallback, right? If a roaring bitmap is dense, so if it's greater than the like 6% uniform distributed, or like, if it's sort of heavily dense, then it will just fall back to effectively being a lot of bit sets with a little bit of overhead. But in the kind of narrower cases, it's significantly better. Boom. Yeah, so here's some speed up numbers. And they're kind of like interesting because the speed ups are like quite ridiculous, which is a bit alarming. But basically the reason is because of some of these things, right? So at this 0.01%, the SDDMM that they're using already provides pretty good speed, right? But the problem is that SDDMM really tanks as they go to like 1% up to like the kind of 10% range with the kind of benchmark size I'm using here. So in this case, all of the like roaring is providing the value at the kind of low end, whereas then this gather and doing the kind of small to medium matrix multiply is what's providing the value in the kind of mid range. And then, when you get to kind of, my analysis said about 45%, but like when you get to a certain cutoff point, at that point, you just want to do the full matrix multiply and post filter, and that's about 45%. So yeah, I hope I've stressed to you that, it's interesting that a library that's widely used and is actually the core of many vector databases that you use every day in search engines is so open to like large improvements in quality and performance. Yeah. So, and again, like what's interesting here as well is if you do any work with GPUs, there's often huge amounts of like performance on the table that you can kind of unlock by fiddling with things a bit, let's use a technical term. Yeah. Boom. So yeah, then I'm going to tie this into a more like concrete use case, right? So I hope everyone here is, let's say, familiar with semantic search, right? And semantic search is great in the sense that when you search red car, it finds a red burgundy automobile. It's also great when you search United States and it finds America. It's not so great when you search Max Buckley and you find Mark Buckley or Max Buck. The fuzzy match, you live by the sword, you die by the sword, right? Is both a strength and a weakness in some areas, right? One of the things my team was working on was query understanding, right? From a query, can we identify like key entities? And if we do key entities, can we like use that to kind of find more relevant, more accurate results? And so this kind of shows kind of some of the ideas there. But basically, there's a paper from 2020, 2020? I don't know, 2021, called Entity Questions, right? And so to put this paper in context, when sort of dense retrieval became a thing, when BERT came out and then like SBERT and all these things, people thought like dense retrieval was the greatest thing on earth and that it was just strictly better than sparse retrieval, better than BM25. And then there was a bunch of papers that sort of showed that actually it's not, that it fails in certain cases, that it's, balancing act. And this particular paper was very kind of straightforward and basically showed that when you ask these simple questions like, who is the spouse of someone? what's the birthplace of someone, or what's the child of someone, especially if these someones are like long tail entities, right? These are not like Barack Obama or like George Bush, Tom Cruise, but like they are people, just random people. The model kind of has a fuzzy notion of who they are, right? Like it kind of gets that, oh, that's a kind of Nordic name, and just kind of embeds you in your Nordic name people, or like, I just have a name that starts with an MA, so any kind of Anglo-Saxon MA name will do, So, if you look at what I'm saying in front of, BM25 like really just dominates the DPR. DPR was dense passage retrieval from Meta, Facebook. And DPR was kind of the paper that came before RAG. It was literally like the prequel to RAG. But you see, like the BM25 was really like crushing it. And this was kind of shocking to people. But, what we were kind of looking at was like, well, if we can identify these named entities, right? And specifically here, I would cite this. There's a model called Gliner. It's actually like a HIST. There's a few models. Basically, the idea is this kind of zero-shot named entity recognition. And you tell Gliner, like, highlight the people, and you give it, say, a query. Where was Arve Furset born? I don't even know who that is. It will like identify the sort of span Arve Furset, and you can use that as a person, and you can use that for other things, right? In this case, basically, what we can use that with our inverted index, right? So we can get back our roaring bitmap that corresponds to this person, Arve Furset. And now, what do we want? And again, I suppose what that roaring bitmap corresponded to is this set of like passage IDs or document IDs, right? It says like exactly which documents mention this exact person. Now remember, this inverted index exact phrase match is exactly that. It's an exact phrase match, right? So this is not going to match Arve D Furset, or I don't know, Marv Furset, if you had those in your data set. But what can we do if we have all of these pieces? And one thing we can look at is like, if we combine DPR with this filter set, how well does it do, right? So if we actually did DPR with this name filtered set, it actually does quite a bit better than DPR globally. I don't know, maybe not that surprising, but you're making the problem easier, I suppose. Now, of course, it's losing some of the DPR advantage, right? It's losing that fuzziness, right? So again, it's not going to understand when you say Michael Tyson, the boxer. It's going to think, ooh, that's not Mike Tyson. So that's not great. But bringing it back to this exhaustive search that we were talking about earlier, what if we're doing an exhaustive search, if we are comparing every document to every query to every document, we could also keep track of the top K that matched the hard filter, right? So then instead of having just the top K global, we have the top K global and the top K filtered. So we have two top Ks, and we can do some simple combination, like a reciprocal rank fusion, or you could do like some convex combination of the like distances or whatever, your mileage may vary. Just obviously keep in mind that the second set, the like filtered set, will be strictly like, in best case, the other one will win. The global set is like unconstrained, right? But anyway, what you find here is, BM25, which was the great golden baseline, they showed in their paper that if you fine-tune dense passage retrieval, then it does better than BM25, right? So this is DPR being fine-tuned on the question formats and the data, so it kind of learns like the formats of the questions. But moving to this sort of name filtered only, again, make things better again, right? What you see. But if you actually combine the name filtering with the reciprocal rank fusion, suddenly you get much better results again, right? So you see that we're now like getting both in one pass. And what's nice again here is, as we'll go on the next slide, is that we can potentially do this for like no additional cost. So because we're doing that sort of exhaustive search, we can just like literally keep track of an additional top K for almost no cost. So yeah, and by doing the union, we're also mitigating the problem of like recall, right? So even though Michael Tyson will not match the documents about the boxer, the fuzzy match will get lots of documents about Mike Tyson, because it will kind of realize the semantic error. So I mean, again, this is work in progress, but interesting. And the filter is adding some degree of precision, right? If someone has explicitly given us a name, then probably we should honor its explicit format. Yeah, and so this is basically the idea about fusing this, right? That like we don't need to do two passes, right? We don't need to do find the top K and now filter and find the top K. We can just like find both top Ks in one pass. I don't have some numbers here, but effectively it looks like it took, costs about 5% more to do the two, right? So, we're getting a very small additional overhead to get two top Ks and get the kind of nice results improvement. And that was even without fully probably optimizing it further, right? So yeah, it's one basic kernel launch, collects two top Ks. And again, hopefully all of these things will be open sourced into CUDA vector search very soon. I mean, so you can play with them if you're interested. Boom. Yeah. So basically, the idea here is that we're kind of combining this like exact match precision with the sort of fuzzy matching, and I'm calling this like deep hybrid retrieval. Yeah, like basically the idea is I need to compare it to Sebastian Bruch's like hybrid retrieval paper, obviously to kind of see what the kind of difference in the kind of performance is. But yeah, effectively it's like just leveraging these things that we already have in search engines or in databases, right? Like we have these roaring bitmaps. Combining these elements, let's say obviously we're at Exa, we're very much like semantic native, like we're kind of building a kind of modern search engine. But that still means you can kind of leverage the best of the past and the best of the present. Yeah. And yeah, so I've linked lots of things to check out, like entity questions paper. You can look at my GitHub if you want to see what I'm cooking there. The roaring bitmaps papers are great. And if you don't know NVIDIA CUDA vector search, really do check that out. It's really useful. Like if you're doing all sorts of like machine learning work, it's quite powerful, quite performant. Oh, there we go. Any questions?
If you have any questions, please raise your hand.
Thanks. First off, I want to say lovely talk. It was very informative. I just want to understand a little more. I don't think I fully understood the roaring bitmaps paradigm. The idea is you have all your data loosely organized, and there's some process, this roaring bitmaps process, that basically converts everything into 64K chunks and then decides what type of container it should be. And then, of course, I guess launches its own individual processes to convert each container into a self-identified, either, what was it? I think you had array, bit set, and RLE encoding style, basically. Is that the basic understanding of what's going on there?
Yeah, so the first part is like, the roaring bitmaps are typically constructed kind of offline. Like if you use something like Elasticsearch, right, you have your documents and you've converted them into some sort of shards, and you say, okay, I've got 200 million documents in the shard. And then offline, you construct this like inverted index for every word in your corpus, or in that shard at least. You keep track of what documents contain that ID. And then for those, instead of storing it as a list of IDs, you convert that list of IDs into a roaring bitmap. So for words like the and, you're just going to get like a kind of useless roaring bitmap that matches basically all the documents. For more obscure words, or especially for like bigrams or trigrams, like you saw with the name example, the bigrams are going to be tiny. They're going to be like super selective. Unless you have Barack Obama or something, you're going to match like sub 0.1%, right? But yeah, so that's typically done offline. That's done by, if you use like Elastic or any of these kind of search providers, like that was index time compute done and you have it. The point about the handover to the GPU is, instead of copying to the GPU a bit set, or even copying a roaring bitmap and converting it while you move it, you could copy the roaring bitmap. And so the GPU then has the roaring bitmap resident. And when it's doing its work, right, instead of like saying, okay, we have 200 million documents, however we want to split this, you now have 64,000 containers. And each container has a type. And each of those types is sort of suitable for different types of workload, right? So if you have an array container, like you have a list of integers, then you should do potentially this SDDMM, right? For that particular one. If you have a bit set, then you should do the like post, the like big matmul and post filter. If you have a run container, then you can basically just do a small gem, for just that run. And so, potentially you can get like a big speed up, especially if in the sort of lower end of the scale, right? The smaller stuff.
Fair.
Yeah.
Just one quick follow-up. I mean, I'm not a search expert at all, but I guess the downside potentially to these roaring bitmaps is that it puts more computation at indexing time, and in theory, adding more documents can get pretty expensive if you have to reorganize all these containers by adding, I don't know, an extra 10% of documents, and suddenly the organization. I haven't fully thought through this, not that I really know, but it seems like that could be a potential downside consequence to that. Is that roughly intuitively correct? Or
I mean, absolutely. I mean,
Okay.
if you think about like, a world in which you just have like no index and you just like grep over everything, that's obviously awesome, but it doesn't scale. You obviously do a lot of work to make it scale, and like roaring bitmaps and like this inverted index is like the heart of lexical search, right? It's like what was being done from, I don't know, the 70s till, So you are doing that. I mean, even the embeddings themselves, right? Like even if you want to use a flat index, and I said there's no index building, you still have to go through the activity of embedding the document and then putting that embedding somewhere so that it's contiguous with the rest of the data, such that it can be kind of like in VRAM and the GPU ready to do the big map model, right? Because those speeds that I mentioned, those very, very nice speeds, they are reliant on it being in GPU VRAM. Like they are reliant on the super high memory bandwidth of your whatever you're using.
thanks. Very
You're
clear.
welcome.
Is there other question?
I'm just wondering how it performs for like complex reasoning intensive queries. Like, I mean, you gave example for some entity-based questions, but yeah, how does it perform for?
So, I mean, it doesn't is the answer. So like this type of work isn't exactly the level where I would expect to go for like a reasoning type question. Like what you want to do nowadays, I guess what the SOTA there would be to have like an LLM do some kind of like query decomposition and potentially some kind of like sequential querying, right?
Mm-hmm.
If you said like, I don't know, what was the top selling album the year Max Buckley was born? You can embed that, and unless the embedding knows the year I was born and then just points you to there and you just magically get like the top selling albums of 1987, it's just ambitious. What you could do is instead have what year was Max Buckley born, and hopefully you find a document that says a year, like, I don't know, on my Twitter or something. And then maybe you take that year and say, what were the top selling albums of that year? So the reasoning is kind of a higher level up the stack. But coming back to that exact example, this would help at that first step where you said, what year was Max Buckley born? Because you're now up ranking the documents that mention exactly me and not some random mark,
Right. Thank you.
Okay, since the time's up right now, we'll have to end this presentation. Thank you for your presentation, Max Buckley. So the next session, we'll have Luca from EPFL talking about latent interaction models.
Thank you, and hi everyone. So I'm gonna speak about a latent interaction model, or how you might better know as multi-vector models. All right, let me start from something that we all know. So like the core idea of single vector retrieval is essentially that every chunk of text can be embedded like in a high dimensional vector in a vector space. And this is computed through passing the text through before like you make tokens, and then you pass from a transformer, then you get embeddings for every token, you apply some sort of pooling to get one single vector, and then you do it both for carry and document, and you can measure some sort of similarity, right? And this is like the classical way to run some pipelines of retrieval where you retrieve and then rank, and this is the first step. And I mean, it's a great success because it's very scalable, because we have very efficient approximated near neighbor algorithms, and it's also it has a lot of variety. We have been a lot of studying around this. I mean, you can find online some open source model about with different scale, different language and domain. So it's very tested pipeline. It's working quite fine. I'm going to question this in this talk, in the sense that I find hard to believe intuitively that like a chunk of text that contains a really varied information, it can talk about many different topics, many different assumptions inside, can be squeezed inside a vector that is close to every similar text, but far from all the other one. I think it's pretending a bit too much ability of like this high dimensional space. I think it's not really feasible. And I think pooling is kind of the problem here because I mean, when you train your model, you have a chunk of text with different information inside, but you're some sort doing training for elastic compression. At the training level, you're kind of teaching the model to select what's the relevant information inside the text you need. And and you do with the training distribution. So when you go live in production, maybe the text you embedded are kind of like a partial view of it. For example, here you see that you have full receipt, but the model has been trained to just focus on ingredients, and that's what you see when you go live. So what happens, for example, when you ask a question about different topics in the text that the model haven't seen? What happens if you embed a longer text because the model has now to compress more information inside the same size vector? Or what happens if you go completely outside of the domain? I think training a pooling, I mean, when you pool, you're essentially trained to discard some information, and it's very hard to generalize, right? Maybe it will be sounding a bit wavy, but I give you a more concrete example. Like Max in his talk already said something about this, but I want to present to you the limit benchmark. This was this year at ICLR, and it's a very toy dataset where essentially all the documents are essentially of this kind, like a person and a list of things he likes. That those are like the things, like very different topics you can find in a text, and that are hard to squeeze inside the single vector. The key instead are very simple. You just ask a simple question: who likes this? And you have roughly like 50 items per person, and in total 1,850 items. And you see that the performance of what we think to be like a very strong embedding single vector model are not quite good at recalling all things. And this is a very simple task, right? While here we see that BM25 is kind of shy of it, but in some sense, this dataset is designed to work for like perfect matching. So I think this is a proxy that tells us that there is something wrong on what you think about like single vector model. We cannot say that this is what is this is like a core component of our retrieval pipeline, right? So since I blame pooling, the core idea would be, why don't we remove pooling? And so I'm presenting here the architecture of Colbert, that is, as my knowledge, like the first model that tried to do that, to go multi-vector. And well, it's very simple. You apply like an embedding pipeline, the encoding pipeline like before, you get tokens both for your query and your document, and instead of pooling, you just apply the maximum similarity operator. The maximum similarity operator is very simple. Essentially, for every token of the query, you measure the similarity against all the tokens of the documents, and finally, you get a big matrix out of it, of similarities, and you take the maximum for every row, so for every across the document embeddings, and you sum over it. So this is a simple formula, and essentially that is the new score of the similarity. Well, this is known as multi-vector because, of course, now to represent a document, you have a multiple set of vectors and not just one like before. But more importantly, it's late interaction, and that's why the talk is named after it. Because the key idea here that enables like these models to perform better is really the fact that you have an interaction at local level of the embeddings. And so the embeddings are now like a local representation of contextualizing the text, but of the original token. And this granularity permits you to have a much better understanding of what's happening if the texts are similar or not. So how did we perform this? I will present you two benchmarks. The first one is BEAR, like it's very common benchmark for evaluating information retrieval. And we see that like late interaction model like works quite well when compared to models of similar size. The red dots are dense models. But of course, like they struggle when you go up in with larger single vector models, because of course those are trained with much more data. They can encode inside them more information. And also, I don't think that anyone has trained such a large model of multi-vector model. You see that like, this is the log scale in the number of parameters. Another data set that is interesting to look at is ProserCom Plus, where essentially it's a reasoning plus a retrieval data set, where you can combine like a strong reasoning model, in this case GPT-5, plus a retriever, and the model can query the retriever and try to get search question, essentially. And depending on which one you use, you get different performance, both in accuracy of the final answer and in the number of calls. And we see that here, like the multi-vector model really shine because they use less code and they have better performance of models that are like, this model is 50 times bigger than both of the two, because those are just 150 million. So that's, I think it's a good proof that this model kind of work. If you are more into the math, there is also a recent paper came out last week that essentially is telling us that the multi-vector embeddings are much more expressive than the single vector. This because even if you concatenate, like you make a single vector that is as big in number of parameters as the multi-vector embedding, this is not enough to approximate well a multi-vector retrieval. And this is kind of surprising. We also have like a math, this in some sense kind of hinting that the multi-vector space is much more complex than a single vector one. It's maybe better suited to represent all the different topics that can be in a text. So it's another proof in that direction. Okay, so I told you these are good models. They work well. Why aren't those everywhere? I mean, we should use them, right? Well, there are actually 3 elephants in the room, not just one. The first one is the vector database size. Now the embedding of a document is a set of vectors. So you can see that the size of your database is exploding. Like you have like maybe hundreds of times the number of vectors to store. The second one is latency, because computing maximum similarity has quadratically more dot products to do. And finally, there is also a problem about tooling, because it's very hard to find code to deploy this model in production. I mean, is not well supported like most of the single vector model, right? So let me just do a sketch of the naive Colbert retrieval. This is how it was first done in the first version of the paper. So when it comes, a new query, you have your database with a lot of all the documents already embedded. It comes a new query, you encode it, and now you have to find the relevant documents. And so what you do, you take each of the embeddings and you retrieve the top K similarity in like a standard vector database. Let's think at face or whatever you want to use. And out of this, you find some relevant documents. Like in the example here, you have document 1 and document C, while the document 2 has no matching, so we excluding from the rest of the pipeline. And finally, you extract from the memory all the documents embedding, because you need those to actually compute the maximum similarity. So this is a very expensive operation in memory, because you have now to read all the documents embeddings that in a standard single vector you wouldn't do. So we see that like the burden of retrieval is much more heavy compared to the single vector. And in this year, people have tried many different solutions. I will just do an overview of what is happening in the multi-vector retrieval, just to give you some buzzword, and there is no time to describe this in details. But some people started working on the database, and well, the core idea here is that the multi-vector embeddings are much more compressible than a single vector one. This because they represent just local information and not the global one. So when you build a database, you can really squeeze and compress a lot in terms of quantization. And essentially now PLAID is the standard database that is used for multi-vector retrieval. And we see that we had a real improvement in the latency. This is like the pipeline I described you before, the simple one. This is the first one, introducing a bit of compression of the embeddings. And this is like one of the last version of PLAID. And it's based like on idea of clustering, in the vector space, and exploiting that for avoiding doing like the second step of so retrieving all the documents embedding. Another idea I want to mention is Tachyon. This is also very new, like I think 2 months ago, and is an idea that very simple, that essentially not all the tokens we embed have the same value, because like the token representing the article there is for sure much less informative than the token saying any other word, like saxophone, for example. So when you build your database, you can like exploit this, deploy more resource towards the the tokens are more informative and less to the one that instead that you think that are not giving too much information. And it's another idea that I think is telling us that this vector space, if you take advantage of the information you have of it, you can get a better retrieval. And this idea will come back later. Other people instead prefer working on the model architecture because Kohlberg is the one first introduced. But for example, I would like to talk to you about XTR. That is something that I'm tinkering a lot these days, so I like to mention. And the idea is very simple. Let's skip the second step, so the retrieval from the memory of all the documents embedding. And let's teach a model, when you train it, to approximate maximum similarity with just the top K that you retrieved. In the end, I mean, if they are already like some sort of top, maybe you don't need to actually retrieve all of them if they are not up into the max, so could work. And finally, a very popular idea is to approximate maximum similarity with some sparse vectors. So one single sparse vector, and this can as SMVA and split. I guess a lot of you here are SAT engineers, so these are cool research ideas, but they want to actually deploy this, to test this. So I would suggest you to download Pilot. This is a library maintained by my collaborator, Antoine, and is essentially built on top of sentence transformer. So it's very similar syntax. If you know how to use sentence transformer, you will be able to use Pilot, and it's compatible with Hugging Face. So you can just download the model from the hub and start test your data pipeline, do your own evaluation on this multi-vector model and see if they could work or not. It includes all the cool idea that I presented to you in the slide before. So yeah, give it a chance. One other good feature of Pilot is that essentially it allows us to scale up the training of a multi-vector model, because before, how do you train a Colbert model? Well, you just take a very strong retriever and you apply some knowledge distillation from another model with the Colbert loss. And that's it. Essentially, you already start from a good embedder and you just adapt it to be a Colbert model. So now that we have Pilot, we can scale up training to do it like much more efficiently. Why don't we try to pre-train a full Colbert model from zero? Do we gain something, or maybe it's not worth because all the information is already there? So with Colbert Zero, we tried to start with modern family of model, not for any particular reason, but just because I mean they came out with many different checkpoints in the pipeline of training of an embedder, and also the data they train on is open source. So we can reproduce the same training pipeline on a Colbert model and see if we gain something. So we had 3 different versions of Colbert Zero, one with a classical just knowledge distillation, one where instead we do the supervised phase, and one where instead we start from the masked language modeling pre-trained model, and we do the full pipeline up to the end. What are the results? Well, maybe not that surprising, because the message is essentially if you train, the longer you train a Colbert model with its Colbert loss, the better. But maybe it's not always worth to do it, because like skipping the very first training step, the one supervised where you do like really contrasted loss on big batches, requires multiple nodes of GPU, is the one that's actually more expensive. It doesn't give you so much gain. So just skipping that and starting to do only 2 phases of training, you see that the gain is not very big, but you get 10% of the cost. And also like the gap you get in the 2 performances based dataset is comparable to the one you get of different compression in your vector database. So maybe you can close the gap in other way. There might be no point of doing all the training. 2 side effects we got is the corresponding single vector model that was trained with the same data. It was actually much worse than the multi-vector, so another signal in favor of multi-vector. And also like Colbert Zero ended up to be kind of the best model for this class of a number of parameters. So there's also another good signal. Now it's not anymore, but another late interaction model has surpassed it. So I think the message is the same. Okay, in the paper you also discuss a thing, this prompt alignment, that is not particularly interesting per se. So the message is, okay, by prompt, I mean like the little chunk of text you had, beginning of the text you're embedding, just to tell the model, oh, this is key, this is the document. And well, the message is just, okay, you should keep it constant during all the training pipeline. Okay, not very surprising. But the funny thing that we found out is essentially that if you evaluate the model with just the prompts, the embeddings of the prompts and not the one from the text, the model still work quite fine. So for example, in this case, if I remove all this part, I leave the embedding on that, I do evaluation just using those tokens, the model perform quite well. We explain this with some sort of implicit query expansion, because the model is able to store like some of most of the relevant information just in the prompts. And the funny thing is that we didn't impose that. The model learned itself to do it. I mean, we didn't have like any penalty in the laws for like telling you store information in this like finest size, because that's another good thing. It's still multi-vector, the prompts, but this finest size, not scaling with the carry length. And in some sort, like the vector space was able to understand that those tokens were free and put information there. This is, you know, some sort of funny effect. I would say that this is one piece of the puzzle that we have to solve. Another piece is, I don't know if you are familiar with the multi-vector literature, but in these days there is a lot of discussion about isotropy, because if you look at the embeddings that you get from a Colbert model, those are very collimated, like pointing very few direction of the adimensional space. So people started wondering, what if I regularize the losses such that they spread around all the possible direction? Do we gain something? And well, the message is yes. At least at first was yes, and came other people say no, like reproducing the same result without doing that. I mean, we are not interested in the particular details, but the message here is that if you impose some geometry constraint in the vector space you go to generate, you can have very different and dramatic effect. And so there is something hidden we are not understanding on this. And finally, even more recently, there is latent errors. This is a paper from Mixed Breed AI, where essentially they train like a sparse autoencoder out of the last layer of first Colbert models, but also from single vector models. And they see that the sparse embedding they find out, they are super good. I mean, they're very good, comparable, like even surpassing the single vector. So in some sense, I reveal that there is a lot of information already there in the vector space generated by the embedding models that we are not using. And it's either traced by pooling or maximum similarity. Maybe it's not doing the right thing, right? So, well, there are some sort of explanation what's happening in the space in some of the paper that I cited, but I don't think there is anyone that's still understanding really what's the deep message inside this vector space. So we should keep research. And I think that multi-vector research here is not like a tool that will solve by itself like the retrieval, but is the tool that allows us to explore this multidimensional space and will allow us, if you, for example, we understand what kind of manifold like text is in this space, it will really enable us to get the new generation of the retriever. That is what we really want, like having a better model retrieval than the single vector and the current multi-vector. So I think this is it. Just to recap, if you want two short-term message to take home, one is download pilot, try out the current status of the multi-vector. If you can give feedback to the community, even negative feedback is a good signal. So please let us know. And in the long term, I think if you're a researcher interested in having like the good generation of a retriever, you should look at the vector space, and multi-vector late interaction is the way to do it. That's it.
Are there any questions? Actually, I have one question because I'm a big fan of late interaction models and multi-vector retrievals. I actually wanted to ask if there's some like some kind of ways that we can avoid anisotropy on the multi-vector retrieval models, something like a GOR loss, you know, the global.
Oh, you're referring to this?
Oh, yeah.
Yes, I think there is this model trained by Top.K that is exactly doing that, putting, forcing an isotropy. This called Colbert, modern Colbert. And yeah, they did this because they are also in vectors SMV, that is the technique of sparsification that I cited before. And they found out that, the traditional modern Colbert was not working well. While if you apply this regularization that you are suggesting, you get good results. But there are some follow-ups saying that actually you don't even need like isotropy is not the key thing, because the people train like some sort of sparsification aware model. So you do the training pipeline with the sparsification as you may attached at the end, and they get models that are even more concentrated, even more anisotropic than the original one, but still working very well with the one with the sparsification technique we are talking about. So that's why I think this is kind of a mystery. We don't know exactly what's happening, and that's still motivating. I think like we should really dig in this vector space, understanding what is deeply happening.
Thank you. I have one more question. What kind of indexes do you use a lot for the multi-vector retrieval models? Something like there's Tacoim you just introduced, and I heard that there's the Movera from Google, right? So what was the best?
There's another technique of like taking a multi-vector model and compressing in like in a single vector of Movera. I'm not sure which index they actually use to power Movera, but yeah, I would say that this falls inside this category. It's not sparse, but a way to approximating like a maxim in some faster way to retrieve than like the full maximum similarity. Personally, I use Plate, like actually the fast Plate implementation that is available with Pilot. But I'm really looking forward to try Tachyon because I think it's a good idea. Yeah.
Okay, thank you. If there's no other questions, I'll move on. Thank you for your presentation, Luca. So the next session, we'll have Seon Bae from Google Cloud Korea introducing Gemini Embedding 2. Please welcome her.
Hi, everyone. Thank you so much for being here. And thank you so much this great opportunity. I'm Solen, and I'm customer engineer at Google Cloud. Today, I'm excited to introduce Gemini Embedding 2 model. But I'm not affiliated with DeepMind at all. And think of this session as a quick overview about comes from my respects after reading the paper of Gemini Embedding 2. Therefore, please note that I cannot disclose any confidential information related with customers. And also the views expressed today is on my own and do not reflect official Google Cloud's position. So before we begin, here's our agenda. First at all, we'll do a quick recap about embedding. Then I'll discuss what sets Gemini Embedding 2 model apart from other models. Finally, we'll walk through some practical use cases. So let's dive into embedding. As all of you already know, embedding allows us to overcome the limitations of traditional search. We mostly relied on these traditional search strategies, and all of these have limitations. First, with keyword-based matching, there is a high dependency on manual rule tuning and heavy maintenance. So it requires constant effort to keep up the search rules. For example, for maintains the applications, the developer have to keep refactoring the query on the application. Second, manual tagging is inflexible. It leads to high information loss because the data must fit into a small rigid set of categories, and it requires a high amount of manual labor. Finally, we try to ML-based leveling, which operates the process, automate the process. However, because it still operates within the predefined level constraints, the classification is often too broad and leading to misclassification. Ultimately, all these three have the same common things that treat the data as a discrete symbol, which prevents the system from understanding the user's actual intent. Now, I'll talk about what an embedding is. Simply put, an embedding takes unstructured data like words, phrase, or pixels or audio and converts it into a mathematical representation stored as a vector. The core principle is quantifying semantic similarity as distance in a multi-dimensional space. As shown in the graph, there's two positive reviews sharing the similar sentiments and are mapped closely into the upper right. And even though they don't share any similar keywords or words, they are placed in the similar place. And conversely, there's a negative review, which placed far beyond bottom. Like this way, embedding enables our system to understand the actual context and meaning, going far beyond simple keyword matching. So moving to the multimodal embedding this time. Traditional multimodal embedding models only support unimodal inputs. So therefore, to map image and text information together, one must compute text embeddings and image embeddings separately, and then perform a hybrid search. Dialect alignment or operations are impossible because text and image vectors differ in dimensionality and semantic structure. Also, several information distortion and loss occurs when forcefully captioning image to text. So far, we are looked at the limits of the standard embedding model. So now we'll look at how embedding technology has advanced. This image is conceptual illustrate what happens. In high dimensional space, content is grouped by its semantic meaning rather than just file types. For instance, an image showing a cute puppy, and there's a description about this image. They are mapped together in the similar area, and there's another car image, and there's a car code name and the model name of this car also mapped it together. And additionally, there's an image of the dog and the car, which plays between those two areas. By this way, we can search awkward contents based on the semantic meaning. Let's talk again about the standard embedding model. A standard embedding model handles different types of data using late fusion. Late fusion forces conversions of input data, often leads to information distortion. To overcome this limitation, Gemini Embedding 2 introduced an early fusion architecture, enabling a native understanding of data exactly as it is. So this approach processes all modalities like text, image, and video, audio into a same shared latent space, which you can see on the colorful square. Latent space, and this enables us to combine image and text into a single query vector. Now let's dive into step of foundational leap of this model. This current stage is pre-training stage. Unlike other models, this model removes intermediate text conversion or captioning engines. By leveraging Google's multimodal capacities, low visual and acoustic data such as MP3, MP4, or image files is sliced directly into a common computational token unit. For example, if you record a noisy construction site, the model doesn't just filter out the machinery clutter. It's actually used that noise to understand the background environment. So just recording the audio, the Gemini model can understand this record on the construction site. At the same time, it also captures the speaker's emotion or tone or the mood in the unified vector without losing any details through text translation or captioning process. The raw data structure is perfectly preserved at the computational tokens. And the next stage is training stage. Gemini Embedding 2 uses bidirectional understanding, while standard generative model read text unidirectionally to predict the next word, and embedding models operate differently. For grasping the holistic meaning of this input sentence, Gemini Embedding 2 utilize the bidirectional transformer architecture. This allows to understand the deep sentence meaning from both forward and backward direction. And the core pipeline of this training stage consists of 3 stages called multi-stage tuning. In one multi-stage tuning, there's 3 steps. First, they do pre-fine tuning. In this stage, this stage is foundation setups that configures the model's eyes, which is attention, and hands, which can be puller for search optimized architecture before diving into the real fine-tuning. And second, in the next fine-tuning stage, it uses hard negatives for precise boundary adjustment. Hard negatives is a sample of incorrect answers that looks extremely similar to the correct one, and this making the model to learn subtle and high-level differences rather than just making easy guesses. In the final stage, the model is finalized by averaging the weights of each checkpoint called model sweeping. In this model sweeping, all of the checkpoints are based on the epochs, and by averaging these weights, we derive the stable set of weights. Moving to the inferencing part, we finalize the process through mean polling and MRL. Through mean polling, the model calculates the average of the token embedding along the sequence axis. This means along each word. So for example, there is I really love this product sentence. The model adds up the scores of each word vector. For example, the model make the vector of each word I really love this product and adds up all the scores of this vector dimensionality and divides the sum by the total number of tokens. As a result, it generates a single sentence vector that maintains the same size of the original word vectors. That makes this vector evenly capturing the overall context of the sentence. Because mean pooling provides the normalized value, this helps the model train much better than max pooling or CLS token pooling. I will talk about this MRL on the next slide, more details. Through the MRL, its performance degrades gracefully and remains stable when dimensionality decreases. This allows the developers to freely slice embedding down to 128 dimensions, enabling efficient uses tailored to specific service requirements or storage capacity. In this stage, by placing the individual classifiers on each dimensions, the model trains the combined result of loss functions. During this stage, because of the classifier applied to the front and earlier dimensions have more higher relative rates, the model is naturally forced to compress the most critical information into the earlier dimensions during this training stage. Thanks to this stage, we can also implement a hybrid strategy while serving. For example, executing main filtering on the lightweight vectors and using the full dimensions only for the top K re-ranking process. This approach optimizes operational costs. Thanks to these approaches, enables Gemini Embedding 2 to achieve specialized accuracy in multimodal analysis without compromising general performance. As you can see from the spider chart on the screen, This model achieves top-tier results across various modalities, and the key highlight here is its cross-modal capacity in image plus text-to-text retriever, where its score on 71 scoring. So finally, we arrive at the last topic. So last topic is use cases. Moving to this use cases, this breakthrough also enables accurate multimodal media search, precise content recommendations, and real-time content moderation. Beyond this typical applications, this multimodal capacity makes it perfect to advanced anomaly detections, such as in semiconductor, the manufacturing defects on production line. They can detect the defeat of the manufacturing line. Ultimately, it's transform how enterprise interacts with unstructured data, making your operations both smarter and highly cost-effective. So thank you for listening. These are the end of my slide.
Okay. I'm sorry, we will have to skip some QA sessions because we are running out of time. So thank you for Seoul. Thank you for presenting. Everybody can give a clap to her again. So the next session is Seung-Yoon Han. He's from Psionic AI. He will present When Evidence Position Shapes Dense Retrieval. It's a paper submitted to arXiv, and he will present it. Everybody welcome him.
Yeah, hi everyone. I'm Seung-Yoon Han from Psionic AI, where this event is happening at the moment. At the Psionic, I'm researching on like information retrieval, RAG, and all of like interesting topics. So today, I wanted to share my very first research project at Psionic AI, which is related to information retrieval, especially dense retrieval. So yeah, so this is my archive link. If you're interested, you can look into it. Yeah. So just a brief explanation of position bias in dense retrieval. As you know, dense retrievers compare queries and documents to see whether they're semantically similar. And in principle, the semantics should not differ depending on where the evidence is located within a document. But dense retrievers are only good at finding the evidence when it is located at the beginning of documents. So we call it primus bias, the tendency of dense retrievers to prefer evidence at the beginning of documents. And this phenomenon applies to most typical like off-the-shelf retriever. So because of this position bias favoring evidence at the beginning of documents, dense retrievers struggle whenever the key information isn't near the beginning of documents. So this might sound similar to a problem in large language models called loss in the middle phenomenon, but that's usually explained by architectural factors. For example, causal attention, where like early tokens get reused across more computations than later ones, and also the positional encodings like RP, ROPE, which favor more recent tokens through distance decay. But the thing is, these explanations don't work in dense retrievals because bidirectional encoders have no causal attention at all, yet they still show strong primacy bias. And also for example, like Quen embedding, which uses RPE, should favor recent tokens, but it favors early ones instead. So what we tried to see here was not the architecture, but the data these retrievers are trained on. And there has been observations that dense retrievers exhibit position bias when dense retrievers are trained on early skewed data, such as MS Marco, but no prior work explored deeply on like how mid or end skewed data affects the position bias in dense retrievers. If the dense retrievers exhibit position bias towards mid or end evidence. So we try to show that the direction of position bias follows the skew in the training data. And this is our hypothesis. The positional distribution of fine-tuning data shapes retrieval level position bias regardless of architecture. So in order to see whether dense retrievers follow the skew in the training data, we built a pipeline that controls the position of the evidence in 4 steps. First, we start with English Wikipedia, split into length means from 256 to 8K, and each document is divided into 3 equal segments, begin, middle, and end. Then we generate a query for each segment using an LLM prompted to write a query interval only like from that specific segment. And since the prompt alone isn't a guarantee, we verify with 3 cross-encoder rebankers, and all 3 must like agree that the target segment scores at least like 0.3 higher than the next best one. And this gave us about 481K retained pairs, the query document pairs. Finally, we downsample by length and positional cell. So all 4 training sets end up the same size, around like 41K pair each. And it gives us 4 configs, like begin, middle, end, and uniform, which the position of evidence uniformly distributed. And to see whether dense retrievers follow the skew in the training data, regardless of architecture, we employed 8 architecturally diverse models, from encoders to decoders, and spanning various positional encoding schemes and pooling methods. So here we also included a model with no positional encoding, which is Tiny Llama, to test whether explicit position information is even required for the bias to emerge. So we have 4 data distributions, begin, middle, end, and uniform, and 8 models, which gives us 32 experimental runs in total. So here's the main results. Each panel shows a different training config, begin, middle, end, and uniform from the left. And the x-axis is where the evidence actually sits in the test document. So if you look at the begin trained model, trained only like on begin evidence, performance is highest early on, and just falls off as the evidence moves later. And end trained is the mirror image trained only on end evidence, and it climbs as evidence moves later. And middle trained model peaks in the middle. So this bias direction just follows whatever the training data was skewed toward. And this holds across all 8 models, not just one. Then if you look at the uniformly trained model, this MU, the right one, the curve is much flatter. no matter like where the evidence is, performance stays fairly consistent. So training on balanced data substantially reduces the position bias. And this pattern shows up even in Tiny Llama, which has no positional encoding at all. And so the model doesn't need any like explicit signal about position to pick up this bias. And yeah. And so like if skewed data creates the bias, we wanted to see like how the model is robust to position sensitivity. So this is a position sensitivity index, basically like how much a model's performance swings depending on where the evidence is. And it means like lower means more robust on position bias. The gray bars are like each model's worst skewed config. The dark blue bars are uniformly like trained models, and uniform like wins on every single model. Like sensitivity drops from like 57% to 87%. Yeah, and this is not a trade-off. Like uniform also has the best mean performance on like yeah, this is the results. So uniformly like trained models performing like mostly performing better than skewed models, and the PSI is the lowest among the 8 models. But here's the like uncomfortable part. We took like these models to standard beer benchmarks, and on average, the begin bias model actually wins. And on fever, which is like begin skewed benchmark, as we saw, it beats uniform model by like 0.13, yeah. And so yeah, the takeaway is that leaderboard like scores can reflect the benchmarks like own evidence location skew, not actual retrieval robustness. So yeah, and yeah, this is just something happening at the ranking, I mean, embedding level. It's actually, so this experimental setup is we take a document and slide that evidence through like 10 different positions, measuring the query document cosine similarity at each one. And for begin trained models, similarity picks at the very first position. For untrained model, it picks near the end. And so the embedding themselves are reshaping around like wherever the evidence lived during training. So yeah, so there are like 3 things to take away from this talk. One, position bias mostly learned across all 8 architectures we tested, including one with no positional encoding at all. And the direction of bias follows the training data, not the architecture. And second, you can fix the position bias at the data level. So balancing the position of evidence in your training data cuts like positioner sensitivity from 57 to 87% without sacrificing retrieval quality. And third, yeah, like you have to be aware that the standard benchmarks are skewed towards like beginning, so it does not reflect enough of the actual retrieval performance of the models. So one quick self-promotion, but it's actually relevant because everything we just talked about is not just academic for us. We apply the same principle, the position-aware, like balanced data curation. When we train our own production embedding models, we consider the position bias. So ComSat embed Korean 8 billion is currently #1 on the Korean MTB retriever benchmark. And yeah, Japan and actually the 0.3 billion model in Japanese is #1 among public models under 4 billion parameters. So yeah, which is 13 times smaller than the runner-up. Yeah, all 3 models are open on Hugging Face. So if you're interested, then you can try it out. Yeah, so this is pretty much I prepare today. Thank you. Any questions?
Are there any questions?
Yeah, so if I understood correctly, so I mean, training to remove position bias, then it can lead to, I mean, degradation in some, I mean, all the position retrieval quality, right? So maybe, right?
I'm sorry.
So I mean, so you did training, for example, uniform training to, I mean, reduce the position bias, but then it sacrificed some, I mean, accuracy for the early positions.
It's quite controversial, but like in real world, you not be able to know whether the real world documents are chunked in how it's gonna be chunked. So the evidence could be placed in at the beginning or mid or end, but wait. Okay, so this is the standard benchmark. We usually measure the performance of retrieval models. It reflects that the standard benchmarks are skewed towards beginning place. So training the retrieval models using uniformly distributed data. One harm the performance, I guess, as we saw so far.
Yeah, so my follow-up question is then maybe one easy fix could be using small size of chunks. Then for, I mean, when you build index, then maybe in many cases, maybe there, I mean, some chunks there, I mean, the key informations will be in the beginning of the chunk.
So if I understood correctly, it's if you chunk the documents into smaller pieces, for example, 128, it won't suffer from position bias, right?
Yeah, but maybe then, of course, I mean, there's good balance on chunk size and retriever performance, but yeah.
Yeah, it won't harm, it won't exhibit position bias if the chunk is small, but you will have trade-off. You will lose the context of documents or something.
Okay.
Yeah, you can choose. Yeah.
Thank you.
Sure.
Is there other questions? I have one question, since I'm really interested in retrieval. I think the pooling method, changing the pooling method can improve this task, because I saw some landmark pooling from sentence transformers pull request. There was something called landmark pooling, LMK pooling. It was inserting CLS token by 256 tokens. So like you have CLS 256 tokens, CLS 256 tokens, and CLS, and then you pull every CLS token and you mean pull them into one embedding. So I think that might reduce some kind of position bias. Have you thought about these kind of pooling methods?
It's kind of like cross encoding, right? Similar.
No. You
No.
just put CLS into the documents.
Yeah. Like, if I'm not wrong, it sounds like similar to like cross encoding, but prior works found out that the cross encoding re-rankers do not exhibit position bias that much, so it might fix the position bias if like you do the like CLS and document CLS pulling. Yeah.
Okay, thank
Yeah.
you. If there are any questions, then thank you for your presentation, Seung-Yoon. So the session 1 is over, so we'll have some coffee and networking break time. Everyone can just network with other people. You have your name tag here. You can eat some burgers or drinks or snacks here. You can go to the restroom. So network, everyone. 홍보 한번 하시죠. 끝나고
I urge you to like combine the second floor because there's some remaining snacks. Well, there's snacks as well. But like I think it's really chilling place to wanna combine the second floor. So like yeah, you can just make a kind of visit there. Thank you.
We've been talking till the sun rises, laughing at dumb stuff, catching those quick wits. Low-key think you've been under my skin. Kinda feels like more than just friends. Sometimes I'm thinking this might be love. No cap, it's the vibe I've been dreaming of. Maybe it's you, maybe it's us. Like, what if this is love? What if this is love? Your hands in mine and I'm all okay. Hey, even chill nights feel like a holiday. Every little thing's got that glow up hue. Baby, I'm just trying to know you. Sometimes I'm thinking this might be love. No cap, it's the vibe I've been dreaming of. Maybe it's you, maybe it's us. Like, what if this is love? What if this is love? Could be something we can't outgrow. Could be the start of our main character show. Either way, I'm hooked, can't get enough. Like, what if this is love? Sometimes I'm thinking this might be love. No cap, it's the vibe I've been dreaming of. Maybe it's you, maybe it's us. Like, what if this is love? What if this is love? Didn't care much how I came across. Used to show up looking kinda lost, but then you walked in, changed my tone. Don't know how you got in my zone. You look too good, I can't look away. Like the kind of scene that makes your day. And I keep hoping I could say that I'm yours in every way. You laugh once and it throws me off. I try to joke but it comes out soft. You don't see it but you've got me stuck. If you were mine, that'd be my luck. You lean and my brain goes blank. Can't play cool, yeah, I know I say. If I had you, I'd treat you well. Wish you knew how hard I felt. You look too good, I can't look away. Like the kind of scene that makes your day. And I keep hoping I could say that I'm yours in every way. We sit close and I lose the thread. You catch my eyes, get inside my head. I'd give it all just to read your mind. And maybe someday you'll be mine. Woke up with your name on my mind. Sun's out, but you're the real light. Coffee's cold, cause I've been dreaming wide about your smile, yeah, it's stuck on rewind. Every little thing just is different with you. Day feels easy, sky turns a brighter blue. Don't know where we're going, I just wanna stay in this moment with you. All day, yeah, all day. Walking slow, no need to rush the time. Hand in mind, we're crossing all the lines. Heartbeats talking like it knows the truth. Baby, I'm just falling into you. Every little thing just is different with you. Day feels easy, sky turns a brighter blue. Don't know where we're going, I just wanna stay in this moment with you. All day, we don't need the perfect plan. Let's just go where we can. As long as it's with you, I'm good. You're my favorite mood. Every little thing just is different with you. Day feels easy, sky turns a brighter blue. Don't know where we're going, I just wanna stay in this moment with you all day.
I rehearsed this in my head like a million times in bed. Every look you threw my way, was I dreaming, was it fake? You were flirting left and right, I was dying not to bite. Told myself to just stay cool, act like friends, play the Can I tell you something weird? My heart dropped, I froze in fear. But you smiled, leaned in so near and whispered what I needed to hear. Wait, you like me back? Say it again, I might collapse. All this time I played it chill. You were feeling it for real. You like me back? No way, come on. Thought I lost before it's begun. Now I'm texting where you at. You said outside, we're something fast. I was hiding every clue, scared to say I wanted you, but you saw it anyway. Turns out you felt the same. We were dancing on the edge, now we're tangled in this thread, and it's pulling like a spark, right from friends into the heart. Now you say had me since that stupid smile, laugh and blush, it's been a while since a maybe turned so loud into let's not wait it out. Wait, you like me back? Say it again, I might collapse. All this time I played it chill. You were feeling it for real. You like me back? For real, no cap. I've been low-key falling fast. Now I'm grabbing code and keys. You said hurry, come to me. Skies look different tonight, 'cause now we're walking side by side. From maybe someday to now or never. Guess this crush just got way better. You like me back, you like me back. Say it again, I live for that. We don't need to play pretend, it's just us now, let it begin. You like me back, then don't just text. Ring my door, I'll meet you next. Took so long, but here we are. Two dumb hearts, one perfect start.
Said you'd call, so I stayed in late. Left the light on by the front gate. Checked my phone, yeah, 100 times. Guess I fell for my own line. Plans I made turning cold and flat. Half drunk coffee in a paper bag. Didn't think you could play it cool, but I'm learning you're good at breaking the rules. Shaking my head, what did I do? Gave all my night just waiting for you. Built up a dream, now it's fading fast. Guess good things never really last. Shaking my head, how could I miss all of the signs hiding in this? You let me down, left words unsaid. Now I'm here just shaking my head. All your talk had a sugar tone. Didn't see what was underneath stone. Walked right in, took up all my space. Left me here with an empty face. I've been kind, I've been way too fair. Gave you time like it's always there. Now my door's gonna stay locked tight. You won't catch me twice tonight. Shaking my head, what did I do? Gave all my night just waiting for you. Built up a dream, now it's fading fast. Guess good things never really last. Shaking my head, how could I miss all of the signs hiding in this? You let me down, left words unsaid. Now I'm here just shaking my head. You text me sorry like it's all fine, but I'm not falling for the same line. I'm done waiting for yes or no. Time to let this go. Shaking my head, what did I do? Gave all my night just waiting for you. Built up a dream, now it's fading fast. Guess good things never really last. Shaking my head, how could I miss all of the signs hiding in this? You let me down, left words unsaid. Now I'm here just shaking my head. Walking down the street, I see the flowers smile. Every little thing feels like it's worth the while. Sky's got a softer shade today. Feels like the world just knows my way. I'm on my way to you. My heart's in bloom. Every step I take, I'm closer to the room where your eyes will light me up. I know this love's got a gentle glow. People passing by, they hum a happy tune. Even cloudy skies can't hide the afternoon. Every sound feels like a song for two. Everything's sweeter when it's leading to you. It's all so clear when you're near. Nothing to fear. I'm on my way to you. My heart's in bloom. Every step I take, I'm closer to the room where your eyes will light me up. This love's got a gentle glow.
네, 좋습니다.
And I don't need the sun to shine.
아, 근데
Your smile is already mine. Every little thing just falls in place when I see your face. I'm on my way to you. My heart's in bloom. Every step I take, I'm closer to you.
아, 네, 네, 좀 해줄게요.
This love's got
좀, 네, 이거 좀 줄이고 좀 BGM 좀. Hello everyone. We're going to start the next the part of this the meetup. So before we moving on, I just want you to introduce this community. Because Youngjun also introduced about Instruct.KR, which is the core host of this meetup, and then we are just always pursuing the open source research and help each researchers to be conducted by hosting the regular meetups by every month, or if there's some good chances to be discussed with. So basically, Instruct.KR is one of the leading the AI research in community. So that you can just type Instruct.KR on the website, you can just be redirected into the website URL, and then you might be able to join here. Yeah. So I just want you to urge to sign up to Instruct.KR, and you are being able to be a part of the discussions in the Korean Adam community. Okay. So before moving on, I just want you to check where the locations that you're coming from. Are there anyone who have a flight time more than takes more than 4 hours? Cool. Or anyone take more than 8 hours? Okay, 8 hours. 12 hours. Ooh. Who across the Pacific Oceans? Yeah, I think there's lots of folks who are coming from the States or in Europe. Yeah, so I just really want to connect those builders in the Korean community and the community from the outside as well, because I'm also one of the who are trying to be in the ambassadors of the OpenAI Codex and Anthropic Cloud ambassador who had responsibility to take advantage of the both Seoul and I must go in Vancouver, so I always try to connect the both of the best of the continent. So I just always try to mingle with the both best of builders and researchers. Yeah. So I just really want to urge to join up the Instruct.KR. So that's my thing. Okay, Youngjun. Yeah. So this is our Discord.
Okay, thanks for introducing Sigrid. So, actually, we didn't have any coffee, but I just rolled coffee, so I'm really sorry about it. I just heard that there's some pizzas in the second floor, so you can just enjoy whatever you want. You can just go out and eat pizzas during the session, so nobody actually cares about it, and just feel free to do everything. Okay, so the second session, we're going to talk about advanced retrieval and RAG. So the first order of the session 2 is Gyuwon Kim. He's going to talk about a QRank, uncertainty-aware adaptive computation for list-wise re-ranking. And this paper was accepted to NeurIPS 2025, right? Okay, so please welcome Gyuwon Kim.
Okay, hello everyone. Yeah, so my name is Gyuwon Kim, and I'm a fifth year PhD student in computer science at UC Santa Barbara. So it's my great pleasure to present our last year URIS paper titled AQ Rank, Uncertainty-Aware Adaptive Computation for List-Wise Ranking. So this is joint work with Soyoung Yoon, Guyong Cho, and Seungwon Hwang from Seoul National University. Yeah, so in the modern information retriever, multi-stage retrieval is quite standard, which means when a query is given and to get top K documents, for example, top 10 documents, instead of directly retrieving top 10 documents, we first retrieve for enough number of documents, for example, top 1,000 documents, and then use some expensive but accurate model to accurately identify top 10 documents. So then these days also, to do this re-ranking task, LLM-based model is also often used. And LLM-based list-wise ranking is quite effective because it can capture interaction between different documents. But if you imagine like passing multiple long documents to LLM, then it's computationally expensive and also inaccurate because there's a loss in the middle issue. So instead of if you imagine like putting all 1,000 documents into LLM, then it'll be quite challenging tasks. So instead of doing that, you split into multiple subset of documents and then aggregate the ranking results to get the global ranking. So then the issue is, so I will explain the existing methods. So you can imagine, for example, the first sliding window method. If you have 8 candidate documents, then starting from the right side, you apply re-ranking and reorder documents and move these windows to right to left. Then you can, if the local ranking is accurate, then you can think that we will get the top K documents on left side, or maybe like tournament style from the beginning. You split it into multiple groups and then drop some less ranked candidates, and you repeat this process until you reach top K. Then you can also get top K retrieval, top K documents. But the issue is they use a fixed amount of computation regardless of whether query is difficult or documents are similar to each other. So our motivation is depending on query complexity or distribution of documents, we want to put different amount of computation. So for easy query, maybe we want to use small amount of computation, and for hard queries, maybe we want to put more computation to get more accurate top K results. So this is the outline of our AQRank framework. So we model documents relevance using a library called TrueSchool. And then based on that modeling, we choose the subset candidate set to apply ranking based on uncertainty estimation. And then we repeat this process and eventually we get top K results with a smaller amount of computation. So yeah, I will go into detail for each component. So the TrueSchool library, it is originally developed for a multiplayer game. So if you, imagine multiplayer game, then once multiplayers have game and we have outcomes of the game, then we can update user ratings based on the results of the multiplayer game. So in our case, we map documents to players and the results of risk-wise ranking to the outcome of multiplayer match. And so internally, they model user rating as a Bayesian. So it's basically, so here documents relevance is modeled as a Gaussian distribution with a mean and standard deviation. So by modeling this, we can calculate and measure uncertainty about any probability. For example, ranking. So ranking is basically the number of documents that have higher relevance than the target documents. So if you know all the distribution of each document's relevance, then basically you can calculate the rank. So there's math behind it, but we do simply we do some approximation to efficiently calculate the ranking. So probability that some documents has rank K or is belong to top K. So we kind of approximate this probability, and based on that, we choose documents candidates to apply risk-wise ranking. So the key idea is, as we have, different from the previous static heuristic-based baseline, we want to sample uncertain documents. In terms of ranking. So we pick documents whose ranking probabilities are uncertain. Then we apply risk-wise ranking only for those documents and repeat that process. So for after ranking, the relevance of those documents will be more certain. So maybe some documents, their relevance could increase, or some relevance of some documents could decrease based on the results of list-wise ranking. So for each step, we compute this measure, so ranking uncertainty, and based on that, we have some threshold, and based on that, we choose subset of documents, and we split it into multiple on some hyperparameter. For example, we use, for example, 20 documents for each LLM-based ranker, and then we partition it to groups, and then we apply LLM ranking, and based on the results using TrueSchool library, we update relevance of each document, and repeat process until we get accurate list of top K. So as you can see in the figure, this relevance from the first retrieval. So initially, the distribution looks like that. So in the middle, you can see some documents, they have high relevance, and documents they move to low relevance. So we don't want to choose, include them to the candidates for risk-wise ranking. So eventually we get accurate top K list like this. So this is experiment setup. So we evaluate on track deal data sets and different subset of bare data sets. And we mainly experiments on BM25 top 100 as a first stage retrieval, but we experiment on different kinds of retrievers such as sparse, dense, or high retriever, and also changing the size of first stage retrieval to 1000. And also we try different LLM and we mainly evaluate in terms of NDCG at 10 for arbitrary accuracy. And we use the number of rank or call as the efficiency metric. So we want to use small amount of rank or call to achieve high ranking accuracy. And we compare with fixed computation baselines. I explained. And this is the configuration for our method. It's detailed, so you can, I can skip here. So basically, our method, blue line, shows achieves superior trade-off in terms of ranking accuracy and efficiency. So red line is terminal baseline, and the green line is Slido baseline. So with for example, same amount of LLM core, we can achieve a higher ranking accuracy. We did also some analysis. So we measured kind of a proxy measure of a difficulty of query based on symmetrical weighted information gain. And we observed that there's negative correlation between number of calls and the difficulty of queries. So for difficult queries, as we expected, we put more LLM calls, vice versa. And also we did a relation study that by changing some of our hyperparameters or design choices, and we checked that our default settings are good balance to achieve good trade-off. Yeah, so in summary, we propose adaptive computation framework for list-wise ranking based on uncertainty-aware probabilistic relevance modeling via TrueSkill. So the core idea is we focus computational efforts on uncertain documents. And yeah, we achieves better trade-off compared to fixed computation baseline across different settings, retriever settings. Yeah, thank you for listening, and yeah, I'm happy to take any questions.
Please raise your hand if you have any questions. No question. Okay. Thank you once again for your presentation. So the next session will be Sung-Won Shim, Beyond Rag versus Long Context. He will talk about 10 minutes. He will give a lightning talk, and he's from Korea University. Please welcome him.
Hello, my name is Sung Shim in Korea University, and today's my topic is about my paper, Beyond RAG versus Long Context Learning, Destruction-Aware Retrieval for Efficient Knowledge Grounding. I think everybody in here know about the RAG, and the long context means that giving the full database, full passage to the LLM, and believing to LLM to avoid the noise information. And there's some problem in the long context or RAG. The one is when we do our long context prediction, it is so expensive. And also there is a loss in the middle phenomena. And the last one is what we found, and this is our motivation. And when we see in the leftmost, the first column, and that each symbol is the passage, and they are sorted into cosine similarity with the query. And the red X means there is no information to answer the query, and the green O means there is an information to answer the query. And when we look at the second column, that means the result of retriever by using the top N method. And there we can see there is a case that even there's a passage with gold, even there is a gold passage in the retrieved pool, LLM fails to answer well. And when we see a third column and the green purple star, we assume that gold passages, all the gold passages are already retrieved in the retrieval pool. And even in the cases, there's a failed case, the LM fails to answer correctly. And when we see the last column, using only the gold passages cumulatively, there is a cases that LM fails to answer well. And this phenomenon is shown different to the open source LM and closed source LM. So this kind of retriever problem is very unpredictable and have a stochasticity to answer. So what we propose is ELDA, just selecting some range to retrieve. And how it's going on is, given the query and passage, we can compute the cosine similarity distribution using pre-trained embedder. This is actually embedder. And using the cosine similarity distribution input, we give those distribution to our adaptive retriever, what we optimized. And our adaptive retriever pi outputs lower quantile and upper quantile among those cosine similarity distribution. And using that range, we can extract some passage in that range, and we give to prediction LLM to answer about the query. And there will be the output, and we can evaluate it. And whether there will be the evaluation signal, whether the LLM answer correctly or not, we use that signal to update our adaptive retriever by reinforced algorithm, some kinds of reinforcement learning algorithm that maximizes some reward signal. By so on, the blue curve is our trained performance. And actually, we did some Bernoulli approach by selecting each passage to retrieve or not. We actually use band action style. But we also did Bernoulli approach. But in that case, there is many kinds of action combination, and the action space is too large. So our retriever fails to optimize well, and it just becomes too optimized to retrieve all the documents. And this is the LDAS behavior, the learned behavior. And given the black line, the cosine similarity distribution, the input to our policy, when there is a specific portion that seems like there's a critical information to answer the query, our retriever selects those region. And when the cosine similarity distribution is some kind of flat, and it selects to retrieve more information with a risk of distracting effects. And this is our results. You can see a lot of baseline of retriever, and our ALDA's result is in the bottom. Also, I'm not sure you can see the value in the parenthesis. That is a document passage usage ratio relative to this long context approach, which uses the alt passage. And the white column is an average performance of open source LLM. and the brown column is a result of average performance of closed-source LLM. So we can see that our approach LDA shows quite good performance with very small portion of passage uses related to long context LLM. And the one of most interesting part is that the passage uses between the open source LLM and closed source LLM. The open source LLM has quite low long context capability, so the passage uses for those open source LLM is just 0.25, but the closed source LLM has quite good long context capability. So our learned retriever LDA optimized to retrieve more documents. And we also do experiments in ZeroShot. We applied the LDA, learned retriever, from here to this hotpot QA and NQ benchmark. And we also here we can see open source LLM uses the less document and closed source LLM uses more document. Oh, sorry, white column is an average performance of long context approach, and gray column is the RAG using a top five passes, and the last column is our approach. So the conclusion is retrieving is very unpredictable and challenging problem, and our key points lies on the capacity of the target LLM. And we trained on some adaptive retriever LDA to select passages in accordance with LLM's long context capability and that LDA is learned to use lower token uses compared to the long context approach, and that is very efficient to use in practice. Yeah, and this is the QR code of our paper and LinkedIn. Yeah, and thank you so much.
Are there any questions for this paper? Oh.
Hi, thank you for the great presentation. So I'm not sure I understood correctly, but you use different subset of tokens for different layers of model, or
sorry, different
subset of tokens for different layers.
You mean layers of network?
Yeah. Or do you use the same?
Oh, we use the same. Yeah.
Okay. Got it. So then you to calculate the attention score, you just sum all attention patterns and then.
Yeah, attention score will propose some signal about given the cosine similarity distribution, and the cosine similarity distribution will provide signal about where to retrieve like this. And this signal gives to the lower quantile and upper quantile to retrieve that some kind of region.
Yeah, the reason why I'm asking this question is because for different layers or even for different heads, maybe they have different distribution or patterns for right.
Yes.
So, okay, got it. Thank you.
Any more questions? I wanted to ask this similar question. Is it all averaged from the transformer layer? So all the heads and all the layers?
Average?
Is it like, are the attention scores averaged?
Yeah, we use average pooling.
Okay, thank you. If there aren't any questions, I'll move on. Thanks for your presentation, Song. So we had one person who had to present before Jeffrey, but his flight wouldn't let him come here, so I just discarded the slide. And we'll have Jeffrey Kim from Nomadamas. He will talk about journey of AutoRag. Please welcome Jeffrey.
Thanks for the introduction. And hello, guys. I'm Jeffrey, and I want to share a journey of Rotorec. So thank you for inviting me to give us a talk in this event, and it is really pleasure to meet you guys. And I think it was really good sections about the rag papers and everything, and it was so informative. And I think my presentation is maybe the easiest one in this event. So because I want to share my experience about making open source rag frameworks. So I made autorag, and I am making so many open source frameworks nowadays. So I want to introduce myself first. So I made autorag since 2024, and I am making tons of open source projects because I really like open source projects, because I really like to build things and share with people. And actually, I wanted to be a famous person with my open source projects. So I made autorag and autorag research, and also I am known as a K-skill builder in Korea. So maybe many Koreans have heard about the K-skill. So, but today I want to share my journey of autorag as why I started, and what is the autorag, and what is the future of my open source journey. So here is the GitHub star graph of my autorag. So I started my journey at January 2024, and ever since I got many GitHub stars, and it reached 4.8K stars. And after that, I want to make something better than the autorag. So I made autorag research last year, and I am making the 2.0 version of the autorag in this year. So it is like the agent native version of autorag. So I will explain what about it, and why these frameworks is essential to this kind of agent world. So I think this is like autorag trilogy of myself. So why I started it? In 2023, I started a startup in the metaverse market, and everybody knows there was no metaverse, and maybe Zuckerberg really regrets why he changed the name of their company. So I want to really learn something new. So there were so many great genres and great technologies out there, and I selected rag. So I think the best way to learn something new is making something new. So I decided to make some open source project in rag. So but I find out there were already too many frameworks. There was LangChain, there was Llama Index in the rag framework. So I don't want to make another LangChain or another Llama Index. Also, there were so many frameworks about rag evaluation frameworks, like Ragas, TrueLens, or many other rag evaluation packages. So I think, what is the next step of the evaluation? I think there was the AutoML, which is rag optimization. So I decided to make auto rag optimization. So it is called auto rag. So basically, I want to explain a brief introduction of the auto rag. So it is basically get a raw documents like Word files or PDF files, and it parses it, and it creates the evaluation data automatically with the LLMs. And we auto-optimize the whole rag pipeline with that created synthetic data. And we can just deploy it after we optimize our rag pipelines easily. So yeah, it was basically the autorag's full process, and it was really hard to make the synthetic data creation because like 2 years ago, the quality of the open source LLMs or the closed source LLMs is really weak. Nowadays it's really strong, so it is relatively really easy to make the synthetic data set, but it was really hard to make a good quality of synthetic data set. So if you don't have good quality evaluation data set, your whole optimization and whole evaluation process will fail. So actually, it was really hard to get a real golden great reg pipelines with just auto optimization process with the auto reg. But I think it was really great experiment to make these things nowadays. And actually now LLM is really powerful, so you can it is really effective way to use auto reg to optimize the reg pipeline. So but as you can see, the auto reg structure is really quite limited to the advanced reg. So you cannot see any agentic workflows in the auto reg parameters. So you can see the pre-retrieval like query expansions or query decompositions, and also the retrieval phase. We included like hybrid retrieval and also BM225 or vector retrieval. And we have like many post-retrieval processes like re-rankers or passage filters or compressors. Also, we have a generation phase, so we can auto-reg can optimize your prompt. Also, what LLMs or what LLM hyperparameters, like what temperature you can use. And we evaluate each retrieval phase with like record precision, and we can evaluate our final answers. So with these signals, we can optimize the whole reg process, like which module we can use. Like if you want to optimize the re-ranker phase, like you can use whole different lot of like re-rankers, like GINA re-rankers or UPR re-rankers or everything else. And you can automatically select which passage re-ranker you gets the highest record or highest precision with the auto-reg. And actually you can configure this whole pipeline with one YAML files, and it was really great advantage 2 years ago, but nowadays like just Claude or GPT can configure everything just with natural language, but it was real good advantage 2 years ago. And actually you can get dashboard also. But as you can see, this dashboard is really nerdy design, and I have zero taste to the design. So if I was made this dashboard in nowadays, it will be really beautiful because we have Opus models or GPT models. Anyway, so there was really barriers and some disadvantages of auto-reg. So it was locked to advanced reg, and there was an agentic reg in 2 years ago, and I think agentic everybody wants agentic reg right now. So advanced reg is not optimized for the production level, I think. But so it was quite limited. And also, I said earlier, making synthetic evaluation data set is quite hard, right? And it is really hard to make manually also. Also, the last one is because of the auto-reg just limited to the advanced reg, we cannot produce many pipelines and many new research that contains the agentic parts. So I decided to make a new one. I think actually first time I thought maybe making auto-reg to agentic level is really good. But after I tried many days to making auto-reg to the new agentic era, I realized, oh, maybe it is better to make a new one. So I just make new one. So I made auto-reg research. So it is kind of like this auto-reg research concept is like this. So we made all dataset, preprocessor, and all the embeddings. And also, we made all research pipelines about RAG. And you just get your own dataset, or you just bring your own pipeline and just make this beautiful research table just one click. It was like concepts of the auto-reg research. So I wanted to unify the data sets, sort of pipelines in RAG, and also metrics, and easily, I want to use easily. So actually, thanks to the agents, I unifies many data sets and many pipelines in the auto-reg research frameworks. And it is really helpful to just making lots of experiments without coding various pipelines or pre-processing various data sets. Also, we provide pre-embedded data sets, and so you don't need to run the whole embedding models to get an experiment. Like, you can download our whole embedding dataset in the Hugging Face. And actually, after making this auto-reg research, everything has changed. The 2026 has come, and everybody talks about agents. And I'm really shocked about the power of the Opus 4.5 model. And ever since, I am using like Cloud Code codecs like daily, like crazy. And I really love agents, so I made a little bit of agent skill and plugin systems in the auto-reg research also. So you can use auto-reg research really easily with agent skills with your like Hermes agent or Cloud Code. And actually, auto-reg research was a really great for the research process and reproduce the reg results of the other papers, but it was quite limited. Like, it was really good for researchers, but not good for like real world or real engineering challenges. So I decided maybe I have to make another things. What will be? But I didn't know at the first time, but I really think I need to make something great in the agenting era with the reg, because I love reg and I love agents. So maybe reg plus agent is really awesome. So I decided to make one. So that's why I started to make auto-reg 2.0. The basic concept is like this. I want to make the knowledge-based layer for agents. So there are so many memory layer, right? Everybody talks about memory for agents, but I think the search part, information retrieval part for agents is actually missing. Every agent, like Hermes agent, does not using embedding or BM25 search. They just use the file name and use the grep, use the ls, use the terminal commands to find something useful in their local folders or any database and so on. And I really think many people talks that reg is dead and agentic search is the best, but I don't think like that. Vector search or lexical search like BIM225 and all the information retrieval systems has to be integrated to the agent system, because there are so many files, there are so many information out there, and agentic system is slow and is not accurate when our corpus is really big. So I really need to integrate the whole like embedding systems like BM225 to the agents, so agents can really retrieve the accurate answers quickly and fastly and really low cost. So it is like a concept of the whole my Autoreg 2.0 framework. So I want to connect whole storage and parsers of document understanding to the agents. So I want to treat each data source as a kind of agent skill. So if you want to connect with agent with Google Drive or Dropbox, you can just add the Dropbox skill, Google Drive skill, or you can just connect the Telegram skill to search in the Telegram. So, and I want to make the orchestration for search, like Autoreg will convert to the search agent. So Autoreg will orchestrate what search methods, like I want to use the BM25 this time. I want to use hybrid approach this time. Or I want to use the late interaction model this time to retrieve this kind of information, and the orchestrator agent can select what data source they can want to use. And also, I want to integrate the operation level, which is self-evolving optimization group. So I want to record each success retrieval signals or failure retrieval signals. So, and I want that signals will help to improve the search orchestration level to the agents. So actually, the original Autoreg version was the just one-shot search over config search, but I want to be this as a memory-driven and personalization loop for the agent. For agents will search really easily and and I am making this with supporting from the Korean government, the Korean government funding for this open source project, and I am really hard to making this Autoreg 2.0, and so I think the MVP version of this will launch in this month. So everybody looking forward to it. And I will be quick. So there are a few projects in this Autoreg 2.0 frameworks. So this is called MinSync. It is just the incremental indexing framework. I made this in Rust also, and this open source is called Jigg. Jigg is just a file map, and you can see. Actually, the file map means for agents, we summarize every files and make the file map like JSON files, and maps the what is this file and what information is in this file. So it is like a map to the agents to find the accurate files in the big corpus, and it really helps the agent. So you can see the hit rate is increased in the Hermes agent. The row column is the row Hermes agent, and the green part is the Hermes agent with Jigg file maps, and it decreases LM calls and tokens drastically, and the hit rate is increased. So this Jigg is on the GitHub right now and is really helpful to increase the accuracy of the agents, and this open source project will include the Autoreg 2.0 also. Yeah, so I really want to build really great things and really great search agents for the agents. Like my dream is my Hermes agent will never lose any information in my local folder or any data sources. So maybe you can search the Autoreg, and also I am in the Nomadamas, which is this AI open source hacker house located in Seoul. So if you want to feel free to connect or follow our GitHub and everything. Thank you for listening.
Are there any questions? Can I ask you one?
Of course.
I didn't really understand what Jigji was. The purpose of the Jigji. Can you explain one more time?
Jigji is the file map, which is Jigji is just a like JSON file, which is maps that which file has the what information in this. Like if you have a file and there are so many information in the A file, right? And LLM summarize the A file and tells and records the description in the file map in Jigji. So with Jigji, there was a pre-summarized informations in the file map, so LLM really helps to like find the accurate file easily and fastly with the Jigji file map.
Oh, okay, I understood. Thank you.
Okay, thank you.
So there's another coffee and networking break time. You have 15 minutes. So we have burgers and beverages and snacks. You can network everybody. You can go to the second floor. There's pizzas for you. And for the next section, we will now talk about some search applications and agents. So everyone would be excited to see some applications about search, not some research. Yeah. So network, everyone. Hi. There are a lot of people in the second floor. Please come down and listen to the session, please. The next section, session 3, we'll talk about search applications and agents. And Daniel will talk about retrieval for trading agents. So I think this is a really interesting topic. And please welcome Daniel for this retrieval for trading agents. He's from FX Toolkit.
Okay, thank you very much. Okay, this is for next, right?
Yeah.
Okay, and to go back, the small one.
Yeah, this one.
Okay. Okay, greetings everyone. I am Daniel, and I'm from FS Toolkit. As I said, I'm currently building FS Toolkit. Yeah, because I still have a full-time job. So today we've been looking at a couple of things around retriever, search, RAG, and all of that sound very pretty interesting. And I mean, I've learned a couple new things that I might go try, because my presentation is like me trying to apply this RAG into like a trading system, right? It's actually a big question mark. My presentation is a big question mark, because at the end of this, I might realize, oh, maybe I can still try to use a RAG system or go back to my whole deterministic approach, which I am currently doing, because I have already tried experimenting and seeing what could happen. So the whole thing with FS Toolkit, what is FS Toolkit? FS Toolkit is literally a trading automation system that I'm building. Personally, it all started with me trying to explore the trading space in quote. But there's something in the trading space, you see signals, everybody sends signals. Maybe if you're not a good trader like myself, I'm more of an engineer and not a trader, right? So, but like, how do I take all these messy signals from different traders? Some traders will send their signals on Telegram or Discord, but then signals can come in different ways, right? How can I just get the signal, make it a trade, and automate it? Okay, let's build an agent, right? It sounds like a pretty good idea for me. Build an agent so that I don't have to sit and wait for signals and manually execute them, right? But now, to do that, you realize when these messages come, they are not always a complete message, right? When you will see a message like, oh, buy gold now, because I started joining a couple signals from all these so-called gurus on the internet. They'll be like, oh, join my signal group, make money. Most times it could be flop, right? But I needed to test this theory. Is it gonna work or not? But I don't want to manually stay and wait for you to send me a signal every time and tell me to buy gold now or tell me to sell now, and I just execute, right? I needed an agent that could do this. So, but then the problem comes, I started joining multiple groups so I can extract their messages when they come, right? But they come in different formats. Most times they'll be like, some will send a full trading signal, buy gold now, the stop loss will come later. They give you like a TP1, TP2, or like a take profit, right? This is a data that is not complete in itself. It's not a valid trade signal. You probably need to wait, right? So the brilliant idea was to make it a RAG system that would help me execute this trade. Well, like with a RAG system, what you're trying to do is you're trying to understand close similarities. You're trying to fetch this message and see what is the closest. Is this a valid trade signal, right? So I decided, oh, I'm gonna just RAG this thing, right? When a message comes, you want to retrieve like the past channel message, you probably want to prompt like an LLM. LLMs is just going to smooth this thing out. Sometimes it will fill up the gap and try to figure out what it should do, right? And then you pass a structured JSON and execute. Now, this might look great, right? For demo, and it's easy to explain, a model could use. But in terms of execution, it poses a risk. And this is why this risk exists. So because you have to ask a question when a message comes in. is this executable? Is this an update to an existing message that came? Because if, for example, you already told me to buy gold with the current position, and that in itself, I couldn't trade that. It becomes like an executable, but it's an incomplete action in itself. I need to wait for like a stop loss, right? Or like a take profit, or like, yeah, there are so many things. And then I need to even wait to know, is it the direction of the trade? So the brilliant idea was to go the RAG approach, but one thing with RAG is it's great for semantic match, like meanings you are looking for. It's useful for nearby meaning. It help you answer. Then with context, like example can improve. For example, if you say gold, buy gold, in trading, gold in itself, especially in forex, in crypto, it might mean something valid, but in forex, you need to trade in pairs, right? When you say SAU USD, you're literally saying buy gold against the US dollar, right? But when you just say buy gold, semantic meaning might be able to put those two together, right? So you might be able to tell that buy gold means XAU USD, but there are a lot of other things you need to factor in, because similar doesn't mean same, right? And models have this whole smoothing effect. That's the implicit guessing thing. They try to like find a way. And then there's also the latency and cost that I had to factor in, because now every new message adds to the whole system. Like you're trying to create new vectors, and they become something that you could search by, right? So this was not, well, this method was great when I did it at first, and it made sense to like go the RAG way. But I decided, okay, maybe there is another way to do this, right? So I decided that the retrieval layer was going to be for the training, and everything has to go through like a pattern, right? So this is what I mean. Past examples. Okay, so instead of doing past examples, that's past trade in a channel, what a channel is each time I say channel, I'm referring to, think of it as a Discord channel or like a Telegram channel. So for each channel I join, there is most likely set of rules that they already used and most times there could also be noise in these channels, because most of the messages there will not always be signal. It could be something else. It could be saying, oh, we are making profit today. And those are not trade signal. Those are not valid signal. But I need a way to be able to filter all of that out, right? So instead of just taking that, allowing the LLM to, it could be any model, even the best models, but like, if you do this, it won't give you the best result, right? You also have like an execution risk. So what I decided to do is historic messages from a channel would be used to like build a channel profile, right? This is just like a single application of all the millions of things you could do with a retrieval system. So this is basically for trading. I need to point that out. So I needed to build like a rule system from history of messages. So when I connect to a new channel, a new Telegram or Discord channel, I'm trying to get like the last 150 messages, and I'm trying to build like a rule and an alias, a system of alias. I should be able to know, oh, when this is a valid trade, or this, instead of having like semantic meanings, you have actual rules, right? I have actual rules, and then I can build a deterministic parser that can take this rule, and because they are already extracted from a particular channel, it has things like what is a valid trade signal. It knows if I'm sending a trade, there will be languages like buy, there'll be languages like sell, so it has all of that to build rules and to be able to factor out some consistent pattern of noise. So rather than having every single message go through a search and come out on the other end as a valid JSON, and then we validate and trade. We literally needed to build a profile system so that for each channel, there's a way we address that channel separate from. So it made the whole thing a lot better for me. And I had a deterministic parser, and then there will be like a validation phase. So yeah. So what's my current execution step, right? So right now, what I do is Telegram, for example. It could be any source. I'm just using Telegram because that's what I've experimented with for real-time messages. So a signal drops. It's a raw test, and it could be edited. It could be an edit as well. Then what I need to do next with that message is now the context retrieval. In this case, because it's no longer just getting semantic meaning, it is getting like, when you see, it's getting candidates, traits, and hints. What candidate mean is the last message could be something like buy gold, right? It's a trade candidate, but it's not enough to be a full trade, right? And so if you send something like stop loss SL with a number, it knows there's an existing candidate, right? There's an existing candidate that is not yet an executed trade. So we need to be able to determine, we need to fetch all of this context based on the current state, right? And then we need the channel profile to interpret what that message is. Then we go through like the evidence-based extraction, and there's also a fallback with the LLM as well. It could be a very random message that we've never done anything about. That could also be a trade, right? And we don't need a lot of intelligence to do that. The basic model can know if this is a trade signal or not. And then we have like specific validation, more like guardrails, and then an execution profile, which will go through like a queue system. So the memory that would matter in this case for trade would be the active candidate, active trade context, recent symbol, and what the current channel is. So before ever hitting any model, you've gone through a lot of rules, and the whole model is now bounded in a way, right? Because we go through, so there are some processes we go through. I think that's in the next slide, right? So there's like a triage, which is for classification, because you need to know, is this even a trade? Is this a trade signal? Is this just a candidate for an expecting an impending trade, or something that you can update, right? So yeah, for us, or for FS Toolkit, when I talk of a signal memory, this is what I'm referring to. I'm referring to incomplete multi-message setup, right? So like a trade that has multiple steps is automatically an active candidate. Then trade context could be existing trade, because there could be situations where the signal could be move stop loss to break even. There could be messages like that. So move stop loss to break even is a valid execution, but it's only valid if there's an existing active trade that match that context, right? So if not, it is not. It means nothing if there was no active trade. So that's why we need like the active trade context, and then recent symbol hint. Recent symbol hint could be based on, yeah, because move to stop loss or move to break even does not tell you the symbol, does not tell you it's gold, does not tell you it's Euro USD or GBP JPY. I don't want to talk so much about the trading side of things. I want to keep it around this. But yeah, so these are what the memory is like. So the retrieval target is not the answer, right? The retrieval target is like the operational state, because now it's not just about getting, similarities. It's more about getting what is the current state. That's the only time you can make sense of the current signal that you have, right? So So where does the history actually help us, right? For me, the history is more like for building a profile rather than for executing trade. So recent messages like the last 50 to 100 example is more for just generating like a profile with rules and aliases, and then we have like a way to validate a validation circle. So these are a bit deterministic because with trading, there are specific things that you know you're either buying, you're either selling, you're either breaking even, closing a trade, right? Or updating your stop loss and take profit. So because of this bounded situation, it was easier to just build something that would have a set of rules rather than having, rather than basing it on semantic meanings, right? So instead of semantic meaning, we could just learn things like format, single messages versus multiple message structure. That could come from a profile group. We could know that, oh, this profile always sends signal as a single message or as multiple messages. And with that information, you also know things like what are some aliases when they say gold, or is that are you referring to SAUSD, or when you say something like BE, some of them will be like BE break even, but like it won't mean break even for every other group. Some group will say break even in full. So we needed to have like channel specific profiles rather than semantic meanings. Okay, so yeah, I still use LLMs, but for this process and all that. But like the most important thing I found out is, yes, we just need some guides as to how we determine what we need to action, what is an what is a real action, what is a real execution, rather than what is rather than expecting a perfect trade signal from every single message, right? Okay. Yeah, so that brings me to like the end. So lessons for me from this whole thing: retrieval is not always about fourth generation. Sometimes retrieval should produce rules, states, or constraint instead of more like answer to test. This because in this will not apply to every situation. For most situation, you would need semantic meaning um, rather than context based on the state of the current group of signals that you've already received. And also, the use of the history is more like for the pre-runtime is to build a set of rules rather than giving you meanings to what. And then similarity is not always evidence for every situation. Just because something is similar doesn't mean it's the same, right? And also, like a fixed profile sometimes could beat certain prompt because we don't want to have multiple prompting systems just to try to generate, to tell what is a trade, what is not a trade, and whatnot. So that's why this presentation is more of a big question mark, because I've seen a lot today. I've learned a few systems, and I might still experiment on if I can rely on an actual rack system to make something like this. And this is more like an open question to the house. Like with the problem I was trying to solve with this approach, do you think there is a way I can make this a complete rack system? Yeah. So that's it for this particular situation. If there's any question or any opinions or yeah. Okay.
I'll give you the mic.
Thanks. It was a little bit unclear to me. What are the inputs? Is it only trading Discord channels where you always have some entry and stop loss, or is it also, I don't know, Twitter message that Trump is going to war with Iran?
Okay. So if I get you correctly, for this trading systems, right? The goal of this experiment or this part of FS2Kit was to figure out an effective way to like take random messages from a group and know what is a correct trade, what is telling me to trade, because I was trying to build a system that would just connect to any group and know when to trade, when they paste the trade. I don't need to know. But like this group would have lots of messages. It will not always be trade. Some things will be noise, some things would be some things would be noise, some things would be actual trade, yeah, and some would be an update to an existing trade, right? So depending on the current situation, you need to know like when to trade or not trade, and I don't need to be there. Like that's the whole idea here, right?
Okay, so but the Discord channels
Yeah.
that you are in, those are trading Discord channels.
Yes,
right?
yes.
Okay.
It has to be a trading signal.
Okay, right. Now I
Yeah.
get it. And second question, how do you create the parse, or how do you extract the information? Because I can imagine you said that every channel has different like form types of messages. Something in one channel can mean something different in different channel. So do you basically every time call an LLM to extract the information and create
Yes.
something meaningful from it? Some standardized format?
Yeah. Okay. Valid. So yes, there's the whole part where LLM does that thing. I use a very good model for the first profile passing. My initial approach was to pass every single message through an LLM. That doesn't make sense, right? Because if you can have a very properly built profile and know what trade signal means for this channel, right? We would be able to capture a lot without ever going through the LLM, right? So for the very first time I connect a new channel, I am literally training a profile based on LLM. This will go through like some fixed set of prompts, some fixed set of instructions. It's trying to figure out what is a valid trade, what makes up a trade, what are the languages for trade, what are the languages for updates to existing trade, and then we build a set of rules. These are JSON set of rules, and then we also build like a regis parser. Do you get? So all of that is because that profile now exists. Most of the messages that come in, because you're also looking at latency. If a message comes in now, a trade is valid this second, it's not valid in the next 3, 4, 5 seconds. So if everything has to go through an LLM, you would be wasting a lot of time and you might end up entering very wrong signal. That's why we build the profile instead of going through an LLM each time. Yeah.
Okay, thanks.
Yeah, thank you.
Any more questions? Okay, thank you for your presentation, Daniel. So the next, Jui Zhang, she's independent. She'll talk about from AI native search to parallel research. And this is the second session. And please welcome Jui Zhang.
Hello, my name is Juhi, and today I'd like to introduce parallel research that I am making now. So, like, to be honest, like after listening to these like very technical talks, like I was wondering if I'm allowed to stand here, but my talk is from a different angle. That what should the user-facing research workflow looks like. So the parallel research is workspace for refining questions, benching research, and synthesizing the results. So the good research starts with a good question. But the first question a user asks is often not precise enough. And before starting the research, we need to understand what decision this research should support. So who the output is for, like what format is needed and which angle matters most. So this makes the rest of the research process much more focused. And the problem I wanted to solve is this. A normal chat interface is good for asking a question, and get some really good answer. But research is more complicated. So the question changes during the session, and subtopics branch out, and evidence needs to be traced. And at the end, many separate pieces need to be merged back into one coherent answer. So research should not be treated as just a single thread, and it needs workspace for managing multiple research. So the first step is research intake. The system turns a vague request into structured research brief. It organizes the goal, audience, output format, scope, and what should be excluded. So instead of jumping straight into search, the system first clarifies what kind of research we are actually trying to do. And after that, the research is divided into several lanes. A lane is a focused research direction that can run independently. So first we create a brief, and then the system suggests several lanes, or user can make it too. And the end, the results are brought back together through synthesis. A lane is an independent research flow. Each lane has its own question, source, artifact, and synthesis. The key idea is that where the research is still uncertain, the work stays separately. Okay, so now I show you the actual research flow, and here's the question that I'm searching for. The user often start with the broad questions like, how can AI system improve the reliability of complex research tasks? And it is a good starting point, but it is still abstract. So here, the AI does not immediately write an answer or finalize the lanes. Instead, it first narrows the direction of the research. So because the initial question is broad, the AI checks whether the research is meant to support a practical system design, evaluate current limitations, or produce a report that combines methods, risks, and examples. So after clarifying that purpose, the system adds possible research branches as parallel candidates on the right. For example, include task planning, source discovery, evidence quality, or human oversight. The user can include, inspect, or remove these candidates before starting the parallel research. So the selected lanes run on the research board. And instead of answering one large question all at once, different topics run as separate research tasks. So this board shows how the overall research is divided into lanes and how each lane is progressing. So here we're opening one of the research windows running in parallel. Each lane works on a specific subtopics and produces a detailed research result for the topic. And also, this is the verification step. During the research, some information found from sources may still be uncertain. So in that case, the system can double check it with another source, or the user can open its original source and verify it directly. And before the synthesis, the user chooses what research materials to bring in. So we have various lanes of research. So the key point is that the system does not automatically merge everything. The user can choose which research lanes should be included in the final answer. And also then the user can narrow it down further ideas inside each lanes. So instead of bringing the entire lane automatically, the user can choose which conversation or content should be reflected in the final result. After that, user also can choose specific claims and evidence too. And finally, the user chooses the synthesis style too. The same research materials can become different types of outputs. And now, the selected materials are turned into a final answer. These results from different lanes are reorganized into readable structure, so the user can see multiple research directions as one coherent flow. And below, each lane result becomes connected research data linked to the main answer. The flow is preserved, which claim, which source, and which intermediate finding influenced in final answer. So while reading the final result, the user can still go back into the context of parallel research created. And also, these sources can also be checked separately. The final answer is organized for readability, but the user can still go back and see what materials were used. So far, I showed the user-facing research flow, and now I briefly show what happens behind each lane. Each lane is not just a single LLM answers. It works more like a small research workflow. It refines the questions, finds external materials, turns those materials into readable text, and checks important claims, and finally synthesizes the result. This is the actual tool stack behind the workflow. For search, the system uses Exa, and for materials, we use GenaReader and extraction tools to turn them into readable text. And the LLMs are used to refine questions or lanes, organize, gather materials into structured results, check claims, and reconstruct the final pack. For longer, more complex investigations, the system can also use deep research for multi-step source gathering. And throughout the process, the outputs are organized into source chunks, lane artifacts, and claims, and evidence so they can be used again later for synthesis or verification. So these show how the system traces where each answer comes from. Sources are split into smaller source chunks, and those chunks are connected to the lane results and specific claims in the final answer. So the prevenance graph works like an evidence map. It shows which source supported which claim and how each lane contributed to the final answer. Here, the RAG is not just a function for searching document chunks. Source chunks, lane artifacts, claims, evidence, and finally part of the final pack and part of the final report can all become memories. So when parallel research produces results from multiple lanes, users ultimately wanting to know about what is the conclusion, or what should I choose, or which evidence can I trust. So the final research report summarizes the key conclusion, integrates findings from different lanes, and compare options when needed, and keep evidence attached to important claims. To summarize, the workflow of parallel research is narrow the question, branch the research, and verify the claims and synthesize the results back into one final output. And you can find the service at theparallelresearch.com. Thank you so much.
Are there any questions? Okay, thank you, Julie. Okay, so the next presentation, we will have Hyunjae Chung from Postech. He will talk about building a provenance-aware search graph for K-pop images. It will be an interesting subject. Please welcome him.
Hi everyone, I'm Hyunjae. Today, I'll share a search system I built for Raj Eugene's image archive. And yes, Eugene's a K-pop group. That's the data set. This sounds like standard image retriever, query in, similar image out. But the problem I actually cared about is different. Not find me similar photos, but tell me where this photo came from, which event, what date, a broadcast, a fan event, or just a tweet. So the system combines reverse image search, multimodal embeddings, LLM metadata extraction, and metadata-aware re-ranking to make search context-aware, not just appearance-aware. Yeah. The core problem is one line. Visually similar doesn't mean same event. Vector search is genuinely good at outfits, colors, pose, lighting, mood, but two posts can look almost identical and come from completely different events. And photos from the same events can look totally different, just a different angle, crop, or timing. So similarity only gives results that look like, but can be contextually long. What archive search really needs is event variable metadata, event name, date, source, broadcast. Here's the pipeline. We start from low images. Each image goes through reverse image search to collect external evidence. Titles, URLs, snippets, possible dates. In parallel, multimodal embeddings handle vector search and clustering. Then an LLM extracts structured metadata from the image plus that evidence. An event resolver merges the weak signal into one event candidate. Finally, high confidence metadata propagates across the cluster, and results get relinked with both similarity and metadata. So the question shifts from which image looks like similar to which image came from the same real-world context. The reverse image search part does allow the heavy lifting. You simply can infer an event's name or a date from pixels. That information isn't in the image. So instead of making a model guess, I collect clue from the web. I query with the original image or a crop and get back page, title, source URLs, snippets, sometimes published dates. Title might name a music show, or URL tells you whether it came from Twitter, YouTube, or a fan site. None of this is ground truth. It's evidence, but then turns a purely visual problem into an evidence problem, and that's something we can actually work with. Yeah, now the LLM stage, and here's what I'm not doing. I'm not asking for a caption. Honey performing in a blue outfit lead nicely, but you can search it, filter it, or debug it. Instead, the model extracts claim against a fixed scheme into two groups: visual claims, what directly visible, member, outfit, pose; event claims, the context, event's name, date, platform, broadcast. Each claim carries a confidence score and its evidence, so later stages know not just what was inferred, but why. Here, the LLM is a structured extractor, not a caption writer. Event metadata almost never comes from one clean source. One result has the name but no date. Another has a date but an ambiguous title, and a nearby image might already have stronger metadata. The resolver combines all these weak signals, search results, file names, embedding similarity, neighboring claims into one event candidate with a confidence score and an evidence list. The goal isn't to extract every possible string, it's to decide whether the evidence points at the same event, and when source conflict, to lower confidence instead of pretending to be certain. For an archive, wrong metadata is worse than missing metadata. Cluster-based metadata propagation is important things. Yeah. One practical issue, reverse search plus LLM extraction for every single image get very expensive. Luckily, archives are full of near duplicated and same yeah. So once one image has a high confidence metadata, we propagate it to its neighbor instead of repeating the expensive listening. But carries propagation wrecks search quality, so it's it's gated. Cluster membership, embedding similarity, claim confidence, complete check. Metadata only spread inside the high confidence cluster with no conflicting evidence. That at search time, results are re-ranked with both signal of vector similarity plus metadata match, confidence, evidence strength. So the top result isn't just most similar image, it's the one most likely to be correct in context. I'll skip the demo, but you can see in QR code for website. Okay. Here is the QR code for the project page. The demo and details are all there. Still work in progress, but the direction is clear. Search by context, not just appearance. Instead of only answering what does this image look like, the system starting answering where did image come from. Thank you.
I think it would be great if we could watch the demo together.
Okay. 뒤로 넘길게요. 트는 방법을 몰라가지고. 감사합니다. 예. 네. Yeah. When I search Lollapalooza, image of Lollapalooza is showed, and yeah, metadata is come from reverse image search, and similar visual is also provided, and it has also propagated metadata. Yeah, that's demo. Great. Is there any questions?
Thank you for the great talk. I would like to ask that I saw some of the video formed some data in the demo. Does the video is been treated with the same as the image has been processed? So this one just crops this one just crops as an image and just be treated as the image file.
Can you 혹시 죄송한데 번역해 주실 수 있을까요?
한국어로 하겠습니다.
죄송합니다. 감사합니다. 진심으로.
저기 이제 비디오가 있었는데 비디오도 마찬가지 그냥 크롭해서 이미지처럼 들어가는 건지 아니면 비디오를 직접 저기 리스닝 하시는 건지.
GIF 같은 경우는 애니메이티드된 사진은 이제 그냥 첫 번째 프레임으로 이제 검색이 되고 나머지는 다 잘립니다. 그래서 그렇게 작동합니다.
알겠습니다. 감사합니다. Thank you.
감사합니다.
So he answered that for the video data, the first frame is used for the semantic search, right? Yeah. Any more questions? Okay.
So thank you for the presentation. So one thing I think I didn't understood, I didn't understand like clearly was when I put an image and I'm doing the research. Is it doing the research on information from the web, or is doing research on a created data set that you already made, you already indexed in your system?
It's actually crowdsourced from many using fans. They are volunteered for give me an image, and they give me an image, and it's like 18K. Yeah.
But have you indexed the images in your system like before, or it's just like for the system to work, do you have to index images in your system before doing the research?
You mean I clean the image for policy?
Not clean, but index like can the system, like for example, if I put an image or maybe a new idol that is not in your database, is it going to be able to retrieve it through internet, or it has to be, let's say, an idol that is in your database?
혹시 죄송합니다. 번역 한번 부탁드려도 될까요?
제가 이해한 게 맞다면
네네.
다른 아이돌을 이제 입력으로 인덱싱을 했을 때
네.
검색 풀에 넣었을 때도 잘 작동하는지에 대해서 여쭤보시는
네, 그렇습니다.
영어로.
네. Yeah, it works with other data set, or even it's not a human, or if it's dog or cat, it works anyway. Yeah.
Any other questions? Okay. Thank you for your presentation. It was really fun.
Thank you.
Okay, the last section of session 3, we'll have Kevin Sun talking about Beyond the Coding Agent. Please welcome Kevin.
Thank you. Hey guys, my name is Kevin, founder of OpenMagi. So I think this talk will be the least technical ones amongst other, other presentations. But so I saw like these days coding agents are very trendy, and basically everyone is now like if you think about like a year ago, no one was using AI agents for coding, but now everyone is not coding without agents anymore. So the trend has been changing so fast, but the gap I found in this market was that for coding, we are confident enough to delegate a lot of works to AI agents, and coding, because like coding has TDD tests, and like it is easy to tell whether a software is working or not. So, but outside of coding, even though agents have been became like the models and agents have become super smart, I found that like not a lot of people are using AI agents for a more general knowledge work, whether it is accounting or legal work or back office operations or research, and that is the problem that I want to discuss today. So this is an actual failure case of AI agent that I experienced with the latest model. Actually, it was Fable. So when new AI models come out, I always use like something like Cloud Code or Codex to do like a complex execute complex workflow to see how reliable it is in terms of in terms of not only the performance but also executing the work as instructed. And it actually failed in this case where I asked it to review a legal contract and come up with a verdict whether I should sign this or not. And then because the actually I put the PDF not in the clean version, but in something that needs OCR to test it to make the test more complicated. And finally, when the AI when Cloud Code tried to read the contract, some of the pages weren't really readable, so the OCL actually failed. But surprisingly, the AI did come up with the final answer with confidence with the hallucinated clause in the contract. But if you think about it, like Fable is smart enough, and we trust Fable or like even like Opus for everyday tasks like in coding. So this is the question: why is it happening for like other works outside coding? So I don't believe that it is a capability problem. So when it comes to like saying like agents are not reliable or I cannot delegate my work to AI agents, I think there is like two separate nuances here. And one is about capability. Like AI agents can be dumb. Like if you used AI agent a year ago, they weren't reliable in terms of the quality of the output itself, which is basically the performance of the model intelligence and its harness around it. But these days, agents like models are very, very smart, so we don't have capability problem that much. But still, we feel that like AI agents are not good enough yet, and that part I believe comes from the control over the agent. So does it actually stay inside your intent or your policies that something like you put like in the system prompts with a lot of must and never and always and want to make agents comply with the rules. And for the first axis, the capability part, it can be separated into model intelligence and harnesses that something like read before write. We have like plan then execute, so that enforces those kind of rules to make AI agents work better. And combined with the better model intelligence, these days the capability of model agents have enhanced significantly. And also this part is solving itself as models are becoming even much smarter. So these days the harnesses that enforce something like read before write and this kind of like performance harnesses are becoming thinner and thinner. So these days like almost so even for coding agents these days, like a lot of people find a pi useful over more complicated agents like Cloud Code or Codex, because these days models itself are very smart, so you don't need a lot of like complex harnesses. But when it comes to something like I want my agents to classify and record the credibility of the every sources that it cites, or never fill in what you can't read, something like this. These are more of a policy than capability part. Because, for example, for the first policy, which I wrote here as an example, classify and record the credibility of the every source you cite. This could be a list of reputable sources, or it could be like LLM judged with simple prompts. So whether that but any brilliant model can skip these rules, even if you put it in the system prompt, because LLMs are stochastic by nature and non-deterministic and non-predictable. So, but but if you think about it, if you think about the coding environment, we don't feel this as much because coding has a test, and if it passes, it works. If it doesn't, it doesn't. And then there could be like a PR review process and a CI/CD and branch protection. So there are a lot of and because coding is closed loop by nature, a lot of this problem is easily solvable through external infrastructure within coding context. But when it comes to general knowledge work, you don't have a CI for contract review or financial research. So you can, and people try to put a lot of this always and never and a must into system prompts, but it actually never works. I mean, it works, but and as models become smarter, it actually gets better in following the rules in the prompt, but it is still like the LLM itself is not non-deterministic, so it can be never perfectly solved. So in this sense, in terms of the value of control becomes much more important, because in terms, as I mentioned before, the model's capability is already saturating, and like we have like models that are smart enough to do very complex tasks. So, but in terms of the value of control, let's say you want to delegate very complex work to AI agents, and then hopefully you don't have to even review the result, and you might want your agent to review it. In this case, the capability these days, the capability is good enough, so you can there's no bottleneck in that part. But in terms of the value of control, as like the more you delegate to the agent, and the more you let it do like for like long learning sessions, it is very crucial that your agent follows all the rules that you want to enforce to it, or at least when it fails at doing that, you need to be able to see it and audit it. So the more the complex the more the complexity of the the task becomes like more complex, then the more the value of the control rises. And also, like everyone's this requirements and rules or policies are very different. Like someone with a legal background has a very different nevers and always is it in their system prompt compared to financial researcher or back office operators. So they're like each people like it. So this is not something that can't be generalized into general purpose harness, or a model can be learned through training. So that is why each person should have their own like harness that is customized for their policies. And actually, the themes already exist through hooks and managed policies on in Cloud Code or Codex. It is not enough, but like a lot of things can be implemented through this user editable themes. But the gap is that not everyone that can benefit from AI agents are like software engineers. So, but today, if you want to customize your agents with this kind of deterministic control layer, you have to write your code and hooks and implement everything by yourself. So that is why I came up with this idea of a control plane where you can write the policies and rules in plain language rules in natural language, and then the control plane can compile it into deterministic workflow or deterministic control layer and an auditable layer, so that the rules that you write in plain natural language can be a deterministic control layer for your agent. So in my previous example, as I said, like the agent failed at OCR and just came up with wrong like hallucinated clauses. So if I had rules enforceable, deterministically enforceable rules like when you have any unreadable sections gets flagged, and it shouldn't be filled in because every clause needs to quote its source. Then LLM doesn't know that the model can still make mistakes, but then the harness layer, the control plane layer, can reject the transaction so that the model can learn the context and then retry or come up with the honest failure. So this is how it can happen. And also this should be auditable. So you might want to, like, agents can fail, but you need to know if it is failing or not. So we can enforce rules like whenever you do this or whenever this kind of in certain contexts, when you're doing tool calls, you have to always keep the evidence records so that later on we can audit this dashboard. So this was an actual the demo case that I prepared. So this is written in Korean, but basically what I asked to this agent is that it is my Claude code, and I asked if the latest I asked it to check the Tesla's latest quarterly operating income, and if it is over $500 million, then buy 10 shares. So initially it searched the website and Google searched and used the web search tools to find the data. And then when it found the result, it was the 900 million. So it was above 500 million. So it actually tried to use the trading tool to execute the trade. But then I had this rule policy that before executing trade, make sure that the clause, the citation is coming from credible sources, which is basically like official IR materials or Edgar official like 10K report. And then when before the tool trading tool got called, the hook snatched the life cycle and then checked if the 900 million, that number is coming from a credible source, which can be determined by like whitelisted sources or like URLs, or it can be also like generated through LLM judge. So in this case, I used an LLM judge, and that judge said that that should be coming from sec.gov or like official IR. So it blocked it. And then so the agents retried by directly fetching the official IR deck. And then so it was able to the next time it tried, it was able to execute the actual trade. And the whole run was recorded in the audit trail so that you can and so that when I say like when I ask agent, did you actually check this evidence, it is not answering based on its own context or memory. It is actually reading the external audit trail or evidence ledger. So it is more robust against hallucinations. So in the long term, I believe that capability shifts from the vendor. So Claude Code is becoming better. Anthropic models are also becoming better. But the control is not something that the model vendors or the frontier labs can customize for yourself. So that is why I built this control layer that helps you customize the rules for your own workflow. Thank you.
Are there any questions? Okay, thank you, Kevin. So we have final break. We'll have about 10 to 15 minutes because the speakers are arriving here right now. They just arrived from the flight. For the next session, we'll be talking about general models and other like agents or multilingual stuffs. So feel free to network. See you in 15 minutes. Hi, everyone. I'm going to start the final session, session 4, general models and others. I'm having Amir to present scaling multilingual pre-training data pre-processing. So please welcome Amir. Have a good presentation, please. Thank you.
Thank you so much for having me here. My name is Amir Hussein, and I'm a PhD student at LMU Munich, Germany. And today I want to talk about scaling multilingual pre-training data processing. This is part of my PhD dissertation. And today I mostly talk about the languages and the language identification and the pre-processing pipelines. So this is the normal pipeline you have when you want to train a model. So you take your data ready, select the architecture, do your training, and then you're done with your model, and now you start to do the evaluation. All of these stages are important, and in each of them you might have many different questions, research questions to answer. So today we want to talk about only the data, the first part. So we have more than 7,000 languages by standard, and less than top 20 languages are very high resource, and near half of the world actually speaks those. So when talking about the multilinguality, there are two different groups. One, they only care about these top 20 languages, and one for more than these languages. And 44% of these languages are actually endangered, and so by those definitions, there are not much of speakers for these languages. But for the rest of them, at least more than 1,000 users available. And among all of these, all of them are not written. So many of them, for example, in Africa or other places, are just oral languages and never have written. And if, for example, linguistics try to, for example, write them, they only start by writing like the phonetics and how they speak it in Latin. And the important question, like how many of these languages are on the web if I want to train a model or find them. So there is an estimation that among all of these languages, 2,000 of them have some sort of online presentation. So we've observed that if you have enough data and train your model, your test gets better and better. So the more data you have, you can train a better model. But what is the distribution we have for different languages? So there is a good paper, I put it in the footnote here, that tries to distinguish the level of the resource for the different languages. It has 6 categories from the 0 to 5, based on how much unlabeled and labeled data we have for them on the internet. And the size of the gradient, each one of them shows the number of the languages we have. So you see the 0 has the biggest size. So it means most of the languages doesn't have enough labeled data or unlabeled data for the training. But these top 20 languages that we talked about is in the group 5. So for most of these group 5s, you don't have that much of constraint about the data, and you can actually find enough information and data on the web and data sets to train a good model. For example, if I want to talk about the group 1, an example, it could be, for example, Bavarian language, which has an ISO code, like BAR. It has another code in the Glotlag repository. And when you look at the information sheet on the Wikipedia, you see, for example, 15 million people speaks this, and it's part of the Germanic languages.
but you don't have an official model, for example, that speaks this language or understand it. It might understand because it's close to German, but it's not like a dedicated model or data set exists for this language. So about the language data, you want to find a very high quality data to train your model. But what is the definition of the high quality? When you say, okay, my data is high quality, it's very hard to define. Like, do you do some sort of manual inspection? Like, I bring some humans. If they say it's high quality, it's high quality. If it's not, by their definition, it's not. Or for example, you go and train some sort of a model and see how they behave. If it behaves good on your evaluation, then you say, okay, my data in the beginning it was high quality, but you don't account, for example, for contamination. Like, for example, if I make a model and train it on the German data, it still could have a good behavior on the Bavarian task as well, because it's, for example, a simple task like natural language understanding. But it's not because of you had a good Bavarian high quality data. It was because, for example, these two languages was close to each other. So it's very hard to define, and it's a bad, ill-defined word. And the other thing is that where we can find this kind of data, like if I want to scale and have millions of the text and enough domain diversity, no licensing issue, maybe web is a good place that most of the companies try to gather their data from the web, or nowadays maybe also people try to gather data from the books as well. But another problem might arise, that is that the language identification. So you want to build, for example, a model that is good, for example, for many languages, like, for example, GPT style models that understand many languages, that can speak different many languages without separate models. But it's a hard problem as well to solve. So for example, for language identification, we have many different libraries, and many of them has a good, for example, performance in terms of the throughput and memory, but still they are not very perfect. So for example, one of the problems we have in language identification is that they don't have broad coverage. So if you took a Bavarian sentence and feed it to a language identification that only supports 200 languages, it most certainly says, I'm pretty much sure it's German, because among those, because it's a supervised closed set training, so your model always, tries from one of the labels that already is trained, and with a very high confidence, it would say it's just German. But there is a chicken egg problem here in case of the language identification. You need a very good label training data to train an LID. Then you need a good LID to do the language identification on the web to gather the data. And again, you need to create the label data. And again, you need those label data to feed to your, for example, your training. So if you, in the beginning, do not have, for example, enough data in one language, you cannot make a language identification for that language to bring you more data, for example, from the web. So there's a dilemma here. So it's not merely considered for example, top 20 languages, but for example, for the rest of the languages, we might have very clean data. Even if we talk about for example, Wikipedia that supports up to 300 languages, not all of the pages on the low resource languages are clean or not contaminated by the near high resource language or near their high resource cousin. So yeah, So we try to make a language application that works up to 2,000 languages in 2023. And our use case for that was if we train such a language identification, then we can put it on the web, like for example, on the command crawl and see how many data it can bring us. So we tried with the FastText because it was scalable. It's from the 2016 by Meta. We would have many control over the parameters. For the data, we tried to get as much as data possible that exists among the academia, Wikipedia, collaborative translations, and even for some of them, we try to make some synthetic data. For example, there are some certain languages that only is written in one script, and that script only belongs to those. Like for example, Korean, it's written in Hangul, but also no other languages, or perhaps is written in that language. So there are some other languages like this as well, like for example, Silati in Bangladesh. So you can make some synthetic data that whenever your model sees that, since it's just that writing system says it's the only feasible language is that one. But and also we try to add the common noises as sort of a label. So sometimes on the web you see PDF gets a bad encoding and it becomes like a gibberish text. These things also, become available later for the pre-training, but they have some sort of a patterns, and some of the engrams, for example, gets repeated in those, for example, bad encodings, and you could also train on those labels to find them when you are also trying to find a language. We also try to, since the task of the writing system identification is much easier than the language identification, we also try to develop a very small library to find, for example, what is written in the text you give in based on the database. On the other hand, we know that from some resources, what each language is written into. Like, for example, if somebody tell me I wrote a Turkish language in Honey, for example, a script, I would say I don't need it perhaps for this kind of materials, this kind of use case. So we tried, to gather these kind of metadata as well. So our bar label for Bavarian becomes like bar underline Latin, and we don't have any more because it's the only, because it's originally written in only this language. So that's why we try to make sure that every language is written there attested writing system. We publish this in LREC as a resource to help at least find the early noises. The other thing that I just mentioned is that there are sometimes some noises on the web, like for example those that you can see on the top. It's a gibberish text, for example. We need a language identification that returns, for example, it's undetermined, not, for example, provides us with a wrong label like Hungarian language. Or for example, if it's a unknown writing system, or at least we don't know what is the language, at least it says, okay, I'm sure it's the script is cuneiform, not, for example, I would guess it's English. And the other thing is this kind of noises that happens in the, for example, Arabic text, that it's a, you can return it at ZX6 label. That means no linguistic content. So yeah, the other one is our model, and this one is the official model that's used by the NLLB team for their translation system project. One other thing that, for example, you could find if your language identification is a good model or not is that when you've done your labeling with one or two model, then you go and, for example, train some Llama style models to see if the findings of those language identification could help, for example, to get a better score. So we had a bunch of downstream tasks. We here aggregated some score for different languages, and we found, okay, these documents that we were able to, for example, identify had a bigger downstream performance relative to, for example, the previous models. So it's good if your language identification covers more languages, because I mean, our major difference between these two is that we tried to get as much as languages possible into training our model, so we would have less the problems like the like cousin prediction or, for example, contamination between languages. So perhaps you are familiar with the Common Crawl, but Common Crawl, if I want to mention, it's a non-profit organization that each month release a bunch of texts that they gather from the web, and each release it's bigger than the before. For example, here I have one from the 2024 that it's more than the 7 terabyte WED file. So if you only WED file is only the text ones without considering the image. And this is, for example, one basic pipeline that is published by Oscar. So you see, when you process your Common Crawl, your main part would be this language tag and finding the right metadata, because it's a bunch of different tags from different languages, from different websites, and you have no idea what language they are accounted for. So yeah, I mean, we tried to apply our language identification on Common Crawl, and it resulted to this data set, but we did it only for a small amount, and the result was like more than 1,000 languages we could have identified on the web. Then we tried to do it for the FineWeb 2. This is the pipeline we had here. So you see here, there are more than the language filtering pipeline, but perhaps those are much more easier to perform. So you first want to identify your URL, get the data extracted. Common Crawl already has done this for you, but if you want to do a better job, you could have your own extraction, because, like, for example, if you consider a web page, it's very messy. Like, it could have the text could be in very different places. You would have problems like the headers or footer coming to your pre-training data as well. But I mean, there are some libraries that can be helpful in that matter. Then you want to identify your language. Then you can have some filters, console filters, and also the removal of the personal identifications. So one of the problems that we observed is that how much time we have? Yeah, okay. Is that you cannot be sure about your language. What I mean by that is that, so you have this language identification. It's a FastText architecture. FastText is based on like a softmax. You have like 200, let's say, labels. You want to calculate what is the logit and also probability of each language for these text. So the more this model is sure about one language, then you say, okay, probably this data is really for that language. When I say, like, for hello world, I'm 99% sure it's English, but I might say for another text, be sure like 50%. Then you might say, okay, this data is either noisy, or it's probably for another language we don't know yet, or it's not written in the conventional format of the text. That's why, for example, the amount of the confidence on that language is low. But there are also other matters, and that makes it hard to find a good threshold to filter the data. So you might say, okay, over 85%, if it's sure, then it's good. But we observed that for different languages, the behavior is different. And the reason for that is because the different languages have different distance from each other. So for example, if one language like Igbo, if it's so different than the rest of the languages, then when you have real Igbo text, it always says, I'm 100% sure, because it's either this or it's not. But for example, the other languages like KMB Latin or your, for example, they have some close cousins or close languages to them. They might have some, for example, loan words that are shared with them. So that's why it's not always clear if it's this language or the other one. Even 65% confidence in those cases would be enough to, for example, make sure that this is the language, not the other one. But since we don't know that, it could be a problem. And this could be led to the, for example, calibration problem. When you, for example, plot your reliability diagram, you would see, for example, for many of the low confidences, the language is still, for example, correct, but you don't know because you try to increase the amount of the labels you had. So one thing that we try to do is that we try to come by a formula to, based on the different texts that we have, select what is the minimum and maximum, for example, confidence threshold for each language. So we try to apply our language application on the attested tests, attested text for each language that we had, and come up, for example, with this formula to find the best threshold rangings. And as you can see in the, for example, table 16, we tried to show that what will happen when you put your threshold at different stages, like low and high, and in our range, and what would be the, for example, the aggregated score. As you can see, I mean, based on a good threshold, you could get as low as like the aggregated score of the 14.9 till good as, for example, 16.9, 16.1. So it's not always a very straightforward situation how to select your thresholds. And the other thing is that still, after we've done this language identification, after we've done this thresholding, we still had some problems and the contaminations. For example, for some of the languages, we still had many of the data being not written in that language. For example, for GLK, Gilaki, 2% of our data after these mini filters was written in that language. So we come up with the idea of finding the words from the text that we have and already trained our language application, finding the words and engrams that only appear in those languages, and defining a score of the affinity, like these engrams and words only appear in those languages. And when there was enough of those available in our document or sentence, then we would have said, this is really that language. And as you can see, it really makes a difference. And the reason our language application, for example, failed in previous missions was because, for example, when you want to have a language application that is fast enough, you try to use the hash tables that is already implemented in the fast text, and those hash tables could be, for example, 2 engrams led to 1 hash key that that is mapped to 1 embedding. So these kind of things appear, and it could be also serve as a contamination score, like you make sure that how much you have contamination. So for example, for Gilaki, it would fall into the last one, but it also shows that the FineWeb2 is really good in that matter. So yeah, these are the resources that I talked about them. So FineWeb2, I mean, if you want to work on the multilingual data, it's a really good resource, I believe. And it's already processed over all of the 100 common corollary snapshots. And it supports more than 1,000 languages. Thank you so much.
Any questions? Oh.
Hi, I'm Antoine, and it's funny because I was looking at this problem recently. I'm not familiar with it, but I was curious, when you talk about scaling, what I had in mind was like throughput and parallelism. Do you have any?
Yeah.
That's not what you talked about, but do you have any like?
Yeah.
How many sentence? What is it dominated by?
Mhm.
What's true?
Yeah, so yeah, very good question actually. So for example, for this project, as I mentioned, each common crawl data snapshot, if you only consider the text, it's more than 9 terabytes. So we've done this for the 900 terabytes, all the 100 common crawl snapshots. And for example, scaling that part, we run for like a 1 month, 10,000 CPU at the same time. So yeah, I mean, scaling that part also matters, but I meant scaling more on the, for example, increasing the number of the languages, because our predecessors only have done it for at most 200 languages. So we wanted to go higher and see what's the problems that we could observe.
Can I ask another one? You talked about CPU. Can this accelerate on GPU?
Oh, okay. So one thing is that so you want to just provide some real good metadata as fast as possible. That's why we go for the fast text. You could solve the language identification, for example, with a BERT style model as well that run on GPU. But then you need a lot of resources when you want to label. For example, our fast text-based language identification can annotate like 1,300 sentences in 1 second. So you couldn't get like this throughput and this level of the parallelization when you have a GPU-based model. So that's why they try to keep it as low as possible, cost as possible. But yeah, I mean, certainly someone could do it with a GPU. If it's a smaller scale, then it would definitely be much more effective. You're welcome.
Oh, any other questions? Oh.
So thank you for the presentation. So I understand that Glotlead is a text-based language identification. So I also had a question regarding the, let's say, low resource languages that are only, let's say, oral, because some civilization, they don't really have like text data. So I'm curious, how do you approach this kind of low resource languages?
Yeah, completely makes sense. When you actually search on language identification, always both of them appear. Like somebody only works on the oral languages. So for example, I know Meta has a really good model on this. I never actually worked on this area, but definitely the real problem is the data for those. So for example, I know they mostly focus on the biblical data, and for example, to hire different persons or already contacted the institutions that read, for example, the Bible for them for those parts. But there are certainly major problems with that as well, like different accents, different things. But yeah, I mean, it's definitely an important, it has an important application as well.
Okay, thank you, Amir. So the next presentation, Kevin will talk about auto agent, autonomously improve agent harness on any domain. Please welcome Kevin.
Okay, cool. Awesome. So just a quick intro about my company. We're building self-improving agents on your first-party data. And awesome. So there's a couple of levers that you can pull for building on top of your own data. Like one of them is post-training, one of them is context. You can also improve the harness, and that's what we're talking about today. Cool. So it might be useful to actually define what is a agent harness. And we can think about it as the environment that a language model operates in. So these are the components, like it's essentially the loop that controls how the model takes action. So you can see, oh, there's like tooling that you give to the agent. There's context ingestion, so this includes like things like memory, skills, the Claude.md prompting, system prompts. There's the orchestration logic, so like thinking about like how multi-agent systems work with teams, sub-agents, etc., how context compaction works. Also, persisting logic. So this is somewhat tied to like context injection, but having stateful agents, right? Being able to kind of operate on context that exists outside of the kind of agent loop itself. So you can have things like long-running sandboxes, etc. And also kind of observability and verification. So having the agent be able to like run lints, run tests on whatever external actions that it takes. Cool. So again, these are the levers, and the issue we've seen in production while building agents for people is that kind of the space of kind of optimizing a harness is very, very large. You have all of these kind of specific parameters you can tune, right? And all of them are very open-ended. Like system prompts are just full natural language description of how you want the agent to act, its behavior. Tooling as well. Dealing things with like trading. Having very granular tools versus a very general tool, but the agent not knowing how to use it. Things like memory, how memory can both on like in the compaction loop and also externalizing the memory and externalizing state itself. Things like this are very hard to tune, and we can see like things. I think one of the first like formalizations of the agent harness came from Sweet Agent by Princeton, and they kind of defined it as like the agent computer interface. So how the agent actually kind of interacts with its environment. And all of this kind of massively affects how an agent performs on its task. I think the original finding they had was, comparing with just like giving the agent a bash tool versus like, reading, editing, writing, etc. All these extra tools like boosted its performance on Sweetbench by like 64%. So obviously, I think these parameters or these levers like massively affect how an agent actually performs on a specific domain. And yeah, my kind of formalization of how we tackle it is called Auto Agent. So it's a framework that's very minimal by design and very understandable, but allows an kind of outer meta agent to optimize a specific domain, a task agent that will hill climb on a specific domain. Cool. So this is like the fundamental loop. There is a outer optimization agent. So it's called the meta agent. In practice, we just use Codex, Claude Code, whatever coding agent harness you prefer. And there is a task agent. So for those of you kind of more familiar in this space, there is the Darwin-Gödel machine. And this is just a kind of one loop agent system where it self-optimizes itself on a specific task. And this generally has been shown to do well on like coding specific tasks, but it starts to decrease performance when you try to give it a non-coding task, because it makes the implicit assumption that if as the agent gets better at coding, it's also very good at improving itself, and then it also like it ends up improving the task on the coding task. But in our demo, we're actually going to show the performance on a spreadsheet task. So it's outside of the domain of coding, and this ends up being the case where if the meta harness is very good at coding, but the domain specific agent is not performing on a coding task, it's much better to have these two agents be separated than internally as one. Yeah, so essentially this is the setup of Auto Agent. It is an open source repository that you can also run on your specific tasks, but it is composed of a couple of files. So the agent.py file is like how you formally define the task specific agent. So this is running on a like OpenAI SDK, agent SDK or Claude SDK, and it's a very minimal starting point of an agent. So we began with just a simple bash tool, and the goal for the meta harness is to make improvements on this agent.py based off of various rollouts to improve the harness and context engineering to hill climb on the specific task. The program.md is just a directive of where the how the meta agent should think about optimizing the agent.py. And we use a framework called Harbor. It's a way to describe like a benchmark, essentially a bunch of tasks with verifiers. So like think of it as just like a series of input prompts, and then you have the verifiers, which are just unit tests or LLM as judge to see whether a agent successfully completed the task or not. You have the jobs, which are just the agent trajectories based off of how you can read specifically how the agent interacted with the environment, the tool calls, the tool results, the reasoning, to diagnose where specifically the agent went wrong or successfully completed the task. And you have results TSV file, which is a ledger about like this specific rollout was the percentage that the agent succeeded in, percentage of tasks the agent succeeded in. So you can kind of benchmark and roll back to a specific kind of checkpoint of agent.py based off of whether you hit a local max, and you can kind of revert and try different things. Cool. So the fundamental idea is you have the agent edit, the meta agent edit. So think of Claude Code editing the agent.py. Then you run your kind of tasks, your Harbor tasks. This will then generate the logs of and also the results of whether it succeeded on the task or not. You aggregate them together. You can see whether as a whole it improved or stayed the same or worsened on the specific tasks. The meta agent will then read the traces itself to understand, we can go through some examples later, but of where the task-specific agent failed, and then it will either keep or revert the edits that it made, and then it loops back into the edit stage again. And you can kind of run this self-optimizing loop over and over again. Yeah, so what's important is that we encode like a formal verifiers for each specific task. I think this in general in production is just very hard for people to come up with tasks that match the kind of distribution of the use cases that they see just by their own users. But it's important that we formally define these so you have a kind of direction that the
I'm sorry.
Cool. So this is an example of a trace. It's kind of a simple one, but kind of gets you to understand how it would optimize the task-specific agents harness. For instance, when the task agent decides to run like this shell script, right? Right now it just dumps the whole output log into the tool result, and then you can see that with 400 characters, 400K characters of output, the context bloats and might cause some kind of context overhead issues. So the context window bloats and the agent performance falls off. So the meta agent can see this trace and then realize, oh, maybe we should dump it into an external file, and then the task agent can then grep or cat over these over this output file to then be able to not bloat its context window and keep performance higher. So we ran this over 2 separate tasks. Terminal bench is more on the coding side. It just tests the agent using, given just a bash, given terminal access, CLI access, being able to execute a series of tasks, and then spreadsheet bench, which is doing some financial tasks on a spreadsheet. So you can see here on the left side, this is the loop that the agent, these are the different cycles that the agent went through, and you can see that it like drops some. Sometimes it makes an edit and realizes that the performance drops, so then it reverts it to the best scenario, and it keeps climbing and keeps saving the edits that ended up improving the task-specific agent. And here is a diagram of kind of the tree. You can see that like, at each specific point, there's a checkpoint of the current best kind of performance, and then the agent will try to do a couple of optimizations, end up, maybe sometimes it doesn't improve, it hits a wall, and then it just reverts back and continues to try different things until it climbs. Yeah. So there are some interesting actually emergent behaviors that we saw. Like none of these were explicitly kind of prompted into the program, but ended up, the agent ended up finding out how to do this on its own. So one thing is doing like spot checking. We gave it like I think around 24 hours, and we told it that it would take 24 hours to optimize over one of the specific benchmarks, and the agent chose to run like isolated tests for small edits rather than the full suite of tasks. And this is because we have limited amount of compute. It's very expensive to run these benchmarks, and it's just like makes these self edits, run these checks to see whether it improved on the task that failed in the previous iteration, and then continued onwards from there. Also forced verification. So the ended up programming like the task agent to have two specific components. One is the part where it actually executes the task, and then also another iteration where a like checker, essentially a sub agent that like essentially code reviews, executes a code review, writing like tests, etc., to basically check whether the main agent completed it. So after say like 100 turns, it would then run this code review, this reviewer agent, and then being able to self-review and then correct any issues that it found. Things like writing unit tests, also progressive disclosure. That's the example we gave where it externalized the tool result. And yeah, and we're running out of time, so we'll just skip through these. Yeah, but we released this online, I think 2 months ago, so and did pretty well, and I think people are pretty interested in this. It's just a small sample of what having an agent have its own like self-optimization loop can do. There's again lots of other levers that you can tune, but one of them is the harness, and we found it to do quite well. I think there's some issues with overfitting, but you can kind of combat this by having this like other eval set and being able to run these like steering checks in the middle, so it doesn't end up overfitting to the training set. But yeah, that's my presentation.
Any questions?
Hi, I'm Antoine. You talked a little bit about this, like the hill climbing. You need to have an objective. I made a similar experiment recently, and I found it was difficult to craft incentives where all the players cannot game it. I didn't quite understand the explanation when you talked about this. Can you cover how do you make sure that the harness and the meta agent are not like conspiring to increase their score?
Yeah, so this is something that we've like also in general when you interact with a general coding agent and ask it to fix a problem, it oftentimes will find like a very specific targeted solution and not like a generally nice solution. And we did find this actually during the runs. And how we combat this is to have like a similar. We have like a training set that the agent actually sees, and then also a holdout set where we test whether it actually overfitted to the end examples that I saw versus generally holds over all of the tasks. Yeah.
Does it mean you already know the answer, or do you generate like trick questions on demand? Because that's kind of how I was doing it.
Yeah, so the tasks itself are handcrafted or hand selected to make sure that they're high quality. Otherwise, like you don't know. Yeah, like I think LMs are notoriously bad at creating very good tasks are they like you can generate them like on the fly, but like the test that it does generate, we found are not very comprehensive, and I think it requires a bit of more human ingenuity to be able to cover. Yeah.
Okay, we'll have one more question.
So in the case of like having pretty long tasks, so did you think a bit about doing some kind of early evaluation?
Yeah, so actually in the original in our original test, we filtered out for like I think 1 hour of or 30 minutes or 1 hour of how long the task agent took. I would say, yeah, I think having some like mid-session classifiers would be very helpful, just to see like if the agent is completely derailed, then we can just cut it short and not spend the extra like 2 hours trying to finish a long task. Yeah. Cool.
Okay, thank you, everyone. Thank you, Kevin. So next presentation, Naman Goyal will talk about collaborating intelligence, supervising agents you can't fully check. So please welcome Naman.
Yeah, hi everyone. So basically, to introduce this topic, I would like to basically say, like, I would say we are kind of in a collaborative space with AI now, where we are morally just supervising their work, and we wanna, and there's a unequal level of intelligence, I would say. I'm not making very hard claims about that, but I'm saying how can we collaborate better with AI and achieve our tasks sooner or better, and how we can be more confident on the work they are doing. So that's pretty much the talk is gonna be about, and some formal verification of what's happening. So yeah, I believe that's pretty much the main motivation, is that we are now significantly delegating a lot of tasks, including coding, drafting, and even complex workflows. And I believe a lot of times I'm also in this fire and forget mode. I'm kind of like, hey, kind of scan my emails, look the emails you want to respond to, and just draft some good responses, and I will just like send them. But I believe the core issue is not now the capabilities of these agents. It's more of how I can, at scale, verify them better. So this verification part is quite hard. I really don't know if what I delegated them to. A lot of these tasks don't have a very good true objective. And there's not a very easy way of saying whether this task was achieved or not. Maybe in coding, there is a very good way. Coding and math, I would say it's a very good way, because we had verifiers, very good verifiers, we could scale them, and that's how the whole industry started. But for a general task, how can I verify, or at least have some sort of guarantee over verification? And other factors, like if you ask an agent to self-assess its own work, like if I ask Claude or Codex to just look at its own work, it's kind of not very good at verifying their own work. And this actually arises a lot from like the way we train them. So yeah, the talk is gonna talk more about this, but in a higher level, if you understand, we have this concept called chat templates, where each of these agents have a role. And when I'm giving the agent the role of generating a response, it goes in the model thought output in the chat template, and the model is trained to actually assume that model thought output is better than and it cannot like really deviate much from its own produced model thought, versus a user input it can be more adversarial towards. So it's like an inbuilt failure, I would say. And so how can we circumvent these issues? So I would say there are like three major failure modes. So on none of the latest models would produce this failure mode, but like basically, I would say they would produce this failure mode, but not exactly in the same sense. So I just like made it simpler so that everyone can understand. So the first failure mode is basically when it like answers with very high confidence that this is the answer. And I guess 2 years ago this was super popular, but like the assistant gave an answer, but the idea is the assistant being wrong is okay. But when you ask it to basically check again, it was still very confident without like really changing its stance. So that's like a failure mode. Another failure mode is like when it already has the right answer, but you ask and push it back, it kind of like pushes back. It should not. It should not be like made to, like usually these are trained to flatter us. So let's say this was a question where I asked it, hey, is 9.9 or 9.11 larger? And it arrived at the correct answer, which was 9.99. But then later I push it back. And I believe most of these models would not do this, but in certain sense, if you choose another task and make it more complex, and even if it is at the right answer and you push it back, it will like actually get pushed back. So in that sense, this failure mode is still observed. And a lot of time when you ask these models to actually basically just verify their own work and check the computation, they don't really redo the work. They kind of just like based on their belief, they just like output, yeah, I believe this is, I checked, and they will like lie about checking the work. So if you actually ask it to run certain tests, a lot of times I see they don't even run those tests. They just like output very fast that, yeah, it seems like I ran the test and it's successful. So I believe in certain sense, these three failure modes are very compounded together, kind of like makes verification a very hard task. So the main idea is now, like most of the, my effort is spent mostly in the evaluation and testing front, and how we can make this, the biggest topic is like, let's say I have already shipped something. How can I make sure that I can measure this in the right way? And basically, if we go back to the older era, in the older era, humans were the only writing code, and we were able to verify our own work because we were kind of writing very small codes and reviewing them slowly. So we only had limited things to observe. But now, like an agent writes the code, and we kind of like are just there to oversee them. And I would say, as a like a person who's made to verify agents' work, we're kind of like weaker in certain sense than how much the capability agent has at writing and generating. So how can we use our capability more to verify their behavior better is like a hard task. And the goal is neither that we should like fully automate everything, that I'm going to trust this agent to do everything, and not is to make like humans read everything or verify all of their output. So the talk is more about how can you figure out a right balance and mathematically justify for certain tasks. How do you arrive at this balance? So I would argue this, that humans are really not good at generating, but they're really good at verifying, especially for tasks which are very visual based. So if I have a browsing based task, as a human, I can like easily figure out, yeah, this doesn't work. I can click around and figure out. But like for an agent, it takes a little while. So we are actually like somewhat better in verification in certain tasks, in that sense. And so basically, yeah, we're gonna basically talk about how we can measure this, and how even being a weak supervisor, we can still supervise these stronger models. And then we will learn certain patterns on how we can like at scale do them better, where we are not really verifying a lot of things. We are only verifying when there's a need, and we will arrive at how do we verify this need. So I guess we talked about the problem, the three failure modes. And then I'm going to talk about my paper. And I'm going to set up a test bed for this particular like paper. In that sense, I'm going to discuss what the test bed is. And then I'm going to propose a technique. The technique is mostly about adding and deviating the task of proposing the solution and critiquing the solutions to different agent, which a lot of people already do. But how do you find the right critique and proposer pair is the main task. And that's what the paper is about. and then a playbook we can use. So yeah, so the paper is mostly about this field of scalable oversight, where there's this idea that you can have AI models debate each other to arrive at an answer. And what we find is very interesting in the paper, and I'm going to discuss the findings in detail. But basically, usually people have this, that in their setup, they have like a proposer model. It just generates an answer. And then they could be the judge deciding, yeah, this is the answer, or they don't have any judge. In that sense, proposer itself is the judge. And then they just like say whether it's right or not. And the paper is more about how do you find a good critique to critique the proposer's work, and then have an independent judge which will look at the proposer's answer, which will also look at critiques, objects, and then say whether it's wrong or right. And how do you pair this judge and critique well? Because not all pairings actually work out. So we compare two methods. One method is called consultancy. It's like basically when you have a AI model kind of basically just have more compute at test time. So it generates an answer. Think of it as like when you're using Codex with like a higher thinking mode, or Claude with a higher thinking or more effort. So that's consultancy, where the same model is asked to just go on forever. So that's the setting most people use it, I would say. But the other setting is where you have a proposer, then you have a distinct critique. That critique looks at the proposed answer, and they can like talk to each other for a while, or that's what the also paper discovers, that actually making them talk for a while is not that helpful. The more helpful part is actually having the critique take an independent stance from the proposer. And then we arrive at the judge can, in the first case, just look at the original proposer's answer. Here, it actually looks at the whole transcript, and it chooses to agree and not. And we find a big uplift if you find the right critique. So this is the main finding of the paper. So I guess this will take a while to explain. So let's start with this task. Like a general hypothesis says, so on the left of the slash is the critique, which is a higher, bigger model. And on the right of the slash is the judge model. So the judge is weaker by design. That's what we want. Like we want to find a critique which can help this judge. What we find is that not all pairing works. Just putting a bigger critique does not really help the judge. So if you look at the coding task, the GPT OS 120 billion parameter model, it basically gives no help to the judge, and it stays at like 0% left. While the same 120 billion pairing for the GPT actually helps in the math-based task. So what is interesting is probably this. Then when this 20 billion model was being distilled from the 120 billion model, probably all of the coding capabilities got distilled within the 20 billion model for coding, but did not happen for math. And that's why if you pair the math 120 billion GPT, it actually helps the 20 billion in the math task, but not in coding. So in that sense, you really have to make sure that your critique is actually really gonna help that judge. Otherwise, it's like useless to just use your extra compute in adding this critique. And the question is then kind of, we saw it for these samples. So like if I use 3.1 Pro Gemini, it actually helps the 3.1 Flash. The 4.6 Opus helps the 4.5 Opus, not Sonnet, by a big margin, like 14 in the logic tasks. And so how can I actually find what is the, like say whether this pairing will work or not in advance? I want to do this offline in advance, and then actually in the deployment time, then use that pairing well. So the first condition we find in the paper is basically the same GPT example, that you need the critique minus your judge for the classification task. So what you do is just take this GPT OS for your task. So you have a coding task. Use it as a binary classifier to say whether this task, put both of them for judge, and take a negative of their F1 score. So that's what we are plotting here. And we find that as long as there's a skill difference between the critique and the judge on that particular task, then the lift can actually happen on a bigger scale. Otherwise, the lift might not happen. So we've observed that for all these pairings where the critique was actually helping is where there was a capability gap between the critique and the judge. And when there's no gap, there was no lift. But this is not the sufficient condition. Another condition which is required is that the judge should not be a summarizing model. Like if the judge's capability is so low that it just summarizes everything it was put through, it will not really help. You need the judge to actually verify each of the facts which came in the transcript. So if we go back here, so if I have a very bad judge, let's say this judge just looks at the whole transcript and just chooses to summarize. It never objects, or it never chooses to verify any of the work in the transcript. That's a very bad judge. So basically you need both things. You need this critique to be better than the judge on that task. Then only you can add this critique, otherwise there's no part of adding the critique. Second thing, you also need the judge to not just summarize when you put the transcript, to actually verify what was happening. So you can do this offline on smaller set. So you check the condition that the critique's capability is higher than your judge capability, not the proposer. Your proposer and critique can be same capability or various capabilities, but the critique should be higher than your judge capability. And second, your judge should be able to actually, when the critique makes a stance or in the transcript, not just summarize, but actually verify what was being said. Then you will actually have some improvement in using your extra compute. So this is the main finding of the paper. So yeah, basically these two conditions. Condition one is the critique must out-classify the judge in that skill. And second is that the judge should actually verify, not just summarize. And if you have both of them, then you can actually scale your compute very well. And then it will work. And now let's look at actually like this in a smaller set and see how we can realize this. And I'm going to propose a technique on how to realize the results. So first, to actually show that this works, let's pick a very simple task. So I'm going to pick some simple tasks where there are verifiers possible. One of these tasks is game of life. Others are physics-based tasks where the verifiers are invariants, and see whether this technique actually helps or not. So yeah, so basically what we're gonna do is have this test bed where we're gonna measure this oversight. And basically the test bed is that an agent will write the code and produce an artifact. So the coding agent writes the code and it will produce an artifact. Then a weak overseer, which could be us, it could be a judge, or the same coding agent. By just looking at the artifact, it will probably be okay. It will be very hard to say whether it's working or not. But we have like a hidden oracle, which is a deterministic cheap verifier. And we can check whether what we are doing is working or not. And we're not going to ever show this oracle to our coding agent who is doing the work. But we can always rely on this to see whether how far we are from the true objective. So the pipeline is something like this. So let's say I pick the task of game of life. The agent writes the code. Then we run that in the sandbox. And we have hidden from the agent the oracle, which knows exactly what the right output is and the right rule is. And the overseer like actually just sees the final output. And we're going to see why this is a good task. So I'm choosing these open source, open weights model, not open source, but yeah. So our coding agent is this 2.57 billion parameter coder model. Our critique is 2.5 coder, 32 billion. It's bigger than the proposer, but doesn't have to be. But it has to be better than the judge. So actually, the judge is weaker than the critique. I checked it offline on this task, all the tasks. So it's a Llama, 3.18 billion. And I also checked that this judge is actually like not a summarizing model. It at least has certain capability to make its own decision. And I believe these are simple tasks, like most of the people might be aware of them, or they're very easy to verify. So this is something called game of life, where you have like basically at a particular chance, you know what cells are alive. So the alive cells currently are highlighted in the black color, and the cells which are dead are in this white color. And then the cell which is being decided is this blue one. And the rule is very simple. So if this particular blue cell has 3 neighboring alive cells, then it becomes alive for survival. So if there's already a cell which is alive, you need to have at least 2 or 3 life. Otherwise, if there's more than 3 or less than 2, the cell dies. And it's like easy, cheap verification. And how it looks like is, if you have a box, it kind of just stays as a box. If you have like a horizontal bar, it becomes vertical. Otherwise, if you have this glider kind of design, it just moves. So it's very easy to like test offline what's the correct part. But if a coding agent like writes bugging code, usually like in this side, like the left side is the correct side and the right side is like the incorrect side, the code will still execute. So just a verifier who's just checking whether the code execute is like a bad verifier. And that's why I chose this, that the code will anyway execute, but we know, like a hidden oracle knows what's the correct answer offline already. Other task I'm choosing is like a simple physics-based task where you have a property which must be maintained. So there's this Kepler's orbit where you kind of need to maintain this property of basically checking whether the energy and angular momentum is being stable or not. And it's very easy, like the coding agent can like write wrong code and it can still execute, but it will not be the correct physics prop. It will not have the correct invariant. Similarly, there's another task is like this Newton cradle, where you know in advance and you can verify whether this invariant is holding over time, where if you have a good elastic collision, then it's a invariant is holding, otherwise not. So yeah, these are 3 RR settings where we will check the technique I was proposing. And I guess this is just for physics, that you want the invariant to hold across different steps. And basically what we arrive is now, like how we can check on this is this idea that we have, first of all, the proposer, the coding agent, which is writing the code. And here I'm choosing humans as the judge. This another version where I choose that llama model as the judge. And then I have that critique, which was the 32 billion Quen model. And there's a deterministic verifier, which will execute our tests, whatever the critique is saying. And basically, I want to make sure like we understand this well, that not all verifiers are equal. So there's a verifier in game of life. The verifier is population. In that sense, that if the population we can compute in advance already, that after step 60, the population should be 42. I believe that's the correct answer for this. Yeah, so it should be 46. So after step 60, the population should be 46. So it's a very cheap verifier. At every step, you know what is the correct. It's kind of like unit cases in coding. But in physics, the verifier is actually like of a lower quality, I would say. You are checking every step if the property is getting satisfied or not, like the energy is being conserved. If you can't make such kind of verifier for your task, then you can check the process of how the agent arrived at the answer. So that's the third level of verifier. So like initially we'll try to like whenever try to pick a verifier, try to pick for your verifier if you can have like check the exact answer. If you cannot do that, then you try to check whether there's an invariant property which is being held across different steps. And if you can't do that, then you do a behavioral or process check of kind of a verifier. Otherwise, you kind of like need to have a human check first off. Okay. So our full workflow is basically this, that we have a strong agent and then a critique and then a verifier, or we can have the judge actually just choose what to do. And what I find is very interesting, that if I just use the judge alone, it kind of like does a lot of false positive. If I just add the critique, it kind of critiques everything. But if I pair the critique and verifier rightly with the judge, we kind of reduce our false positives a lot. And the main idea is that the critique is the proposer model to generate hypothesis, which then needs to be verified by the verifier. And a lot of these hypotheses might not be right. So that's why just putting the idea, like I guess this is a idea used for a long while, that you need to have a high recall model paired with a higher precision model. So the high recall is the critique and high precision is the verifier to actually help you. And still you cannot really rely on the model's own confidence. So for choosing the task where it should actually go to the humans, I cannot just rely on the model's own agreement. So if I ask the model to say whether this should be escalated to the human, it's kind of very random. So it doesn't really matter, like that's useless, I would say. And in all our cases, our verifier was still like not a true oracle in that sense. So it can happen that the population check in the game of life can still pass and the model can cheat. So it can cheat in this way. It can like just spoof around and this will happen. But if you use the correct like critique, then probably you can get past this by even having that bad verifier of just checking the population size. So I will propose how you should use this technique is to just start with like a Claude.md or agents.md requirements file where you have an acceptance criteria. And you just ask one thing, ask the agent to look at and open that requirements file. So in this case, let's say I pick the task of monthly active users and the agent should just check for final total matches the billing dashboard for active users. So just add a one runnable check that you ask the agent to actually open that report and check the final total to the billing dashboard. And so that's like you start small, then you kind of like prompt it to make your judge better. So instead of like checking if the judge prompt is like default to pass, like basically you don't have any judge, but whatever the coding agents decide it's fine. You kind of add a judge, which would be like you pair Claude with like a shop hook, and in that shop hook you ask it to critique itself. So you add a shop hook in that sense. Other thing is you can add an independent critique. So I can ask one Claude model to actually call another Claude or Codex model to actually be a critique. And the critique should not be like, hey, just find some edge cases. It should actually give out what are some claims, why it might be wrong, and what checks to do in that sense. So, and then you have a verifier. So you kind of can build your verifier. The verifier could be unit test for coding. For browsing, you can like actually have a very strong verifier who actually checks the dates and stuff, or it could be just like a weaker first check. So you can have various levels of verifier for your task, and then you make them paired well. And that's how I would say that this is the main flow that you should probably focus on building. That I start with a strong agent. Initially, I will not have any judge, or the judge would be just to accept the answers. Then you kind of add a weak judge, which would be like a stop hook. And then you add a critique, an independent critique. And then you pair that critique with the verifier. And that's how you kind of like supervise the task better. Yeah. So basically, in nutshell, I will like end in this way that what you need is basically you kind of reduce your agent's work to claims, and then you just check those claims.
Thanks for your presentation. We're really sorry that our presentation is a bit delayed. So if you have any questions, you can just ask Naman in the back. And I'm very thankful for your presentation, Naman. So we have final presentation right now. Ben Kim is going to give a lightning talk about Game Engine Bench, evaluating coding models on real runtime environments. Please welcome Ben.
Thank you. I'll keep it brief. I think everyone looks a little bit tired or ready to go home. But yeah, so this is actually an unreleased benchmark. Let me give a bit of an intro. I run a company called Nitrode. And what we do is we try to advance game development with AI using frontier AI research. And for this benchmark, we had a couple of collaborators, including 4 of us from Nitrode, as well as the head of applied AI at Nexon, as well as a couple of researchers from Columbia and Cornell. And yeah, we're excited to present Game Engine Bench, which is basically, in our view, the best representation of coding with an enterprise game development and the benchmark that's designed to reflect that. So the biggest thing first is that, well, the pass rate here is the best pass rate was 55.5%, and it was done by Claude Fable with a material leap over the number 2. I'll get to the results in a bit. But the way that the passes were calculated were actually different than your standard coding benchmark. Oh. So the first one here is that the model cannot just compile. It has to also behave and also function in a game in and of itself. Games actually function differently than standard coding benchmarks for 4 reasons. The first one here is that the referee rule. So in an online game, it can't just reflect on the client side. So for example, if like you attack somebody or you shoot somebody and you take damage or you do damage, if the only thing reflected is on the client side, then hackers or cheaters can manipulate the games relentlessly, which is why you get stuff like Escape from Tarkov, because their anti-cheat is only on the client side. So as a result, we took a look at 4 different things in order for a test to pass. The first one is the referee rule. The second thing is the sync. So for example, if a door opens for one side, the other side on a third-party server also has to open. And the third is like life or death, i.e. if you die on one screen, you have to die on the other screen. So in real runtime environments, the actual environments for the test to actually occur has to go beyond just compiling. So let's go straight in. The test was built from 9 real Unreal Engine projects. We actually got direct advice from Nexon on how to format it for enterprise game development workflows, so that there's about 110 tasks with a variety of different things. If you go to Nitrode.com, you'll be able to see the GitHub as well as the overall benchmark paper. And we are currently running it on different CLIs as well, so those results will be updated as well. But the biggest thing here is that every task starts with an existing game. A feature is removed or a brand new feature is written by us or by experienced game developers. And then the model's task, after it's given a specific plain text prompt, is to create tests as well as create that feature from that existing game repo. The evaluations run inside the engine. So after it solves, once the model is done, then the actual checklist is injected and it checks to see if all that checklist is hit. And then the final step is an LLM judge that's scored on a specific rubric to see whether the actual behaviors match the actual outcome that it specifically compiles in. So this is the results. The first one here is that you can clearly see Claude Fable 5 Max completely beat GPT 5.5x high. But the most interesting thing here is that in this benchmark, it was very clear that increased time spent on reasoning drastically increased the performance of each model. So from GPT 5.5x high, as well as if you can see GPT 5.5 medium, there's almost more than a 3x difference in reasoning time and reasoning length between performance. So let me get more into this actually. And this is actually not as apparent as in other agentic coding benchmarks. And we're still trying to exactly figure out the reason why through more tests as to why there's a 3x difference between reasoning capabilities. But we think it's also because game development requires a significant amount of spatial reasoning beyond agentic coding, which I'll touch on here. So not a single model solves the entire benchmark. There were 31 tasks where no model was able to solve any of it. And there was also different tasks that were solved by different models that different models could not solve. So for example, only Claude Fable was able to solve the generated map orchestrators, while GPT 5.5 was the only one that could solve tasks related to the behavior tree. So the most important thing that we actually set to be careful about in this benchmark was to make sure that the tests or the models did not fail because of syntax issues, but rather the failures are behavioral. So the biggest thing here is that every model's failures were actually behaviorals when they actually did fail a test. And the most interesting thing here is that the largest area that the models failed at were actually in save and persistence tags. So when you close out of a game, that the game still saved the progress of the player before, those were the tasks that the models failed at the most, which were actually theoretically the most intuitive. So yeah, as you can expect, the prices for Claude Fable 5 are significantly higher than the cost for GPT 5.5. But the most interesting result we actually had here was that Gemini 3.1 Pro, despite scoring much worse on agentic coding benchmarks overall, actually scored one of the highest in their benchmarks, almost matching Opus 4.8. And we think it comes down to Gemini 3.1 Pro's strong spatial reasoning scores. So if you look at the benchmarks, GPT 5.5 and Gemini 3.1 actually have very similar scores across spatial reasoning, while Opus 4.8 tends to fall behind on spatial reasoning while having very, very strong agentic coding performances. So even though this benchmark was designed to actually test agentic coding capabilities within game development, spatial reasoning was still a key part because there were so many tasks centered around placing objects within spatial games or actually implementing specific tasks. So as you can see here, that Gemini 3.1 Pro, let me flip back to the results here, actually only scored right below GPT 5.5 high. And we thought that was quite of an interesting result. And this is actually bolstered. This is actually not noted within this slide deck here. But the interesting thing here is that we actually have a graph with the benchmark itself as to what each model failed at. And Gemini had one of the highest compile failures, which means it actually failed at agentic coding, but it actually did much better at overall implementations than the other models. So if you notice, other than Fable, Gemini had almost a double compile error compared to GPT 5.5 high, but the results are much closer simply because of Gemini's advancements in spatial reasoning. Yeah, so one of the known limits of this current benchmark here is that the CLIs are all different. And the reason why we took this choice is because most game development enterprises, when they're currently using models, they currently tend to just use the Claude Code CLI, and they tend to compare the harness across like the harness plus the model versus anything else. And for Gemini, it's anti-gravity. But we are also running separate tests with an independent harness right now, which is when we will publish fully, but you can actually see a preliminary version of this benchmark on our website. Yeah, so it looks like frontier agents write really great on real C++. So if you look at GPT 5.5 as well as Fable, their compile errors are almost zero. But when it actually comes to implementing and keeping it running in real runtime environments, they fail over 60% of the time. So as a result, it looks like for game development, agentic coding still has a long way to go, especially because running it at runtime is completely different than just having plausible C++ code. Thank you. Yeah, I think I'll also just take questions after. I think you guys can just come up to me for questions.
Okay, thank you. Thank you, Ben. Okay, so we have a final networking session. You can just go home if you want. And everyone who wants to network, please go to the second floor and network with other people. We'll have to wrap up here, and you can just use the second floor. Thank you for coming, and I'll be at the second floor also. Thank you.